Two of the most precise instruments ever built have been measuring the same universe using different methods, and they keep getting different answers. The gap between those answers is not shrinking. It has been growing for a decade, quietly, in the pages of journals most people will never read, troubling physicists who cannot explain it away. In late 2025, that discrepancy crossed 5 sigma, the statistical threshold physicists use to declare a discovery, the same threshold that confirmed the existence of the Higgs boson. This is not a rounding error. It is not instrument noise. 5 sigma means the chance of this disagreement being a random fluke is less than 1 in 3.5 million. Meanwhile, the James Webb Space Telescope has been finding galaxies in the early universe that should not exist, brighter, more chemically complex, and roughly 100 times more numerous than our best models predicted. And 95% of everything the universe contains is made of something we have never directly detected and do not understand. For decades, cosmologists assumed these were separate puzzles, loose threads at the edges of an otherwise solid picture. Then, in January 2026, a galaxy was confirmed at a distance no instrument had ever reached, existing just 280 million years after the beginning of time, and it looked nothing like anything our models said should be there. These are not loose threads, they are the same thread, and tonight we are going to pull it, tracing the universe from the surface of this planet to the edge of everything light has ever reached, confronting the dark scaffold that holds 95% of reality together, standing inside a void 330 million light-years wide, and asking the oldest question there is from a vantage point nobody has ever had before. If this is the kind of journey you want to take, subscribe and come along. We do this every week. The universe is larger than you think. The model is shakier than anyone is comfortable admitting. Let's begin. Go outside tonight. Find a dark place away from the streetlights if you can. A garden, a field, a car park on the edge of town. Look up. Give your eyes 10 minutes to adjust and wait for the sky to reveal itself. On a clear night, far from any city, you will see somewhere between 2,000 and 4,000 stars. They will appear to stretch from horizon to horizon. They will feel infinite. They will feel like you are looking at the universe itself, spread out above you in all its depth and grandeur. You are not. Almost every star visible to your naked eye is within roughly 1,000 light-years of Earth. 1,000 light-years sounds vast. The Milky Way galaxy is 100,000 light-years across. That means, on the clearest night of your life, standing in the darkest place you can find, you are seeing approximately 1% of the diameter of your own galaxy. That is all. 1% of one galaxy out of 2 trillion. The Milky Way contains an estimated 250 billion stars. On that perfect dark night, you can see about 4,000 of them. That is like standing in New York City, being able to see a single building through the haze and calling it the skyline. Now consider what lies beyond that single building. The observable universe, the portion of the cosmos from which light has had time to reach us since the beginning, contains an estimated 2 trillion galaxies. 2 trillion. Each one holding hundreds of billions, or in some cases trillions, of stars. The total number of stars in the observable universe is estimated at 10 to the power of 24. That is a 1 followed by 24 zeros. There are more stars in the observable universe than there are grains of sand on every beach and every desert on this planet, combined. The entire surface of the Earth covered in sand, and then that number again, and again, and again. The stars outnumber the grains. The night sky is not a window into the cosmos. It is a peephole into your neighborhood. This might seem like a matter of scale, an interesting comparison between what we can see and what actually exists. But it has an implication that goes deeper than scale. Everything we know about the universe, everything our models of cosmology are built on, is derived from observations made through that peephole. Our picture of what the universe is, how it works, how it began, and where it is going, all of it is built from data gathered at a vantage point that by cosmic standards is a dust speck. For most of the 20th century, physicists were comfortable with that. The models held, the predictions matched the observations. Cosmology became, in the words of its practitioners, a precision science. Then the measurements got better, and the precision revealed a crack. The crack centers on a single number, the most important number in all of cosmology. It is called the Hubble constant. Edwin Hubble, working at the Mount Wilson Observatory in California in the 1920s, made one of the most consequential discoveries in the history of science. He demonstrated that the faint smudges of light scattered across the sky, the nebulae, astronomers called them, were not clouds of gas inside the Milky Way. They were separate galaxies, each containing billions of stars, lying at distances so enormous they dwarfed everything previously imagined. And they were moving away from us, not because they were flying through space, but because space itself was stretching, carrying the galaxies apart the way dots on the surface of a balloon are carried apart when you inflate it. The universe was expanding. The Hubble constant describes the rate of that expansion. It tells us, for every unit of distance between two galaxies, how fast those galaxies are receding from each other due to the stretching of space. Get this number right, and the rest of cosmology falls into place. It gives you the age of the universe, how long the expansion has been running. It gives you the size of the observable universe. It gives you the fate of everything, whether space will expand forever or eventually, over incomprehensible timescales, slow and stop. Get it wrong, and everything unravels. For most of the history of modern cosmology, the Hubble constant was imprecisely known. There were arguments, sometimes heated ones, about whether it was closer to 50 or closer to 100 in the units cosmologists used to measure it. Then, in the late 1990s and the 2000s, precision instruments arrived, and the uncertainty shrank dramatically. By the 2010s, two separate methods of measuring it had become extraordinarily refined. Both were painstaking. Both used the best instruments available, and they gave two different answers. The first method looks backward in time. The European Space Agency's Planck satellite spent years mapping the cosmic microwave background, the faint afterglow of the Big Bang, the oldest light in the universe, released 380,000 years after the universe began, when the primordial plasma of the early cosmos finally cooled enough for neutral atoms to form and light to travel freely for the first time. The pattern of tiny temperature variations in that ancient light encodes the physics of the early universe with extraordinary fidelity. Feed that data into the standard model of cosmology, and it produces a value for the Hubble constant of approximately 67.4 kilometers per second per megaparsec. What that means, in plain terms, is that for every 3.3 million light-years of distance between two galaxies, those galaxies are receding from each other at 67.4 kilometers per second. The second method looks at the nearby universe as it is today. Astronomers measure distances to a class of variable stars, stars that pulse with a regularity directly tied to their true luminosity, so that comparing how bright they appear with how bright they actually are tells you precisely how far away they are. From those nearby measurements, they step outward, calibrating progressively more distant objects, eventually reaching a class of exploding stars whose peak brightness is consistent enough to serve as measuring sticks across billions of light years. This is the cosmic distance ladder, a chain of calibrations, each rung anchored to the one below it, reaching across the observable universe. The most precise measurement in this tradition was published in 2025 by Dan Skolnick and colleagues at Duke University, who used an unusually careful new calibration of the Coma cluster of galaxies as the ladder's first rung. Their result, 76.5 kilometers per second per megaparsec, 67.4 against 76.5, a difference of about 9%. In everyday life, 9% is negligible. In cosmology, it is the difference between a universe that behaves as we understand it and a universe that does not. To understand why physicists are troubled, you need to understand what 5 sigma means. When a result in physics reaches 5 sigma, the probability of that result being a statistical fluke, a chance coincidence of measurement errors rather than a real difference, falls below 1 in 3.5 million. 5 sigma is the threshold that was required before physicists would announce the discovery of the Higgs boson in 2012, the particle that the standard model of particle physics had predicted for nearly 50 years. 5 sigma is what physicists mean when they say something is settled. By late 2025, the discrepancy between the two Hubble constant measurements had reached that threshold. Not 4 sigma, not 4.5, 5. Neither team has found an error that explains it away. The James Webb Space Telescope was used in 2024 and 2025 to re-observe the variable stars the local measurements relied upon, specifically to test whether dust or crowding in distant galaxies had contaminated the brightness readings. The answer was clear. The measurements were accurate. The local value stands. And while doing this, James Webb was also finding something no one had predicted. Before it launched, the standard model of cosmology expected a relatively sparse early universe. A small number of well-formed galaxies appearing gradually over hundreds of millions of years after the Big Bang. What the telescope found instead was roughly 100 times more bright, well-developed galaxies than the models allowed for. Brighter than they should be, more massive than they should be, more chemically complex than they should have had time to become. Not one anomalous galaxy, but hundreds, spread across multiple independent surveys. A factor of 100 is not what a small adjustment fixes. So here is where we stand. 2 measurement programs of extraordinary precision, measuring the same fundamental property of the universe, arriving at answers that cannot both be right. A space telescope finding the early universe to be far more structured and far more fecund than our best models predict. And 95% of everything the universe contains made of substances, dark matter, dark energy, that we have never directly detected in any laboratory on Earth. Something is missing from our understanding, something fundamental, sitting not at the edges of our picture, but somewhere near its base. To understand the shape of what we do not yet know, we first need to understand what we do. And that understanding does not begin with abstract constants or distant anomalies. It begins close. It begins with something almost embarrassingly concrete. It begins with how far away things actually are. Start with the moon. It hangs in the sky roughly 384,000 kilometers away, close enough that you can see its surface features with the naked eye, the dark plains and the pale highlands, the scars left by billions of years of impacts. During the Apollo missions, when astronauts on the lunar surface spoke to Mission Control in Houston, there was a delay between every exchange, a pause before every reply, not because of radio technology or bureaucratic procedure, but because a radio signal traveling at the speed of light takes 1.3 seconds to cover the distance from the moon to the Earth. 1.3 seconds. The astronauts heard every question from the ground just over a second after it was asked. That small hesitation, barely noticeable in archived footage, easy to miss, is the sound of distance. Now take that lag and let it grow. Mars, at its closest approach to Earth, is about 3 light minutes away. At its farthest, when the 2 planets are on opposite sides of the Sun, it is closer to 20 light minutes. If you sent a signal to a rover on the Martian surface and waited for confirmation that it had received the message, you might wait 40 minutes for a round trip. Any malfunction, any crisis, any decision that needs to be made on Mars requires the people managing the mission here on Earth to wait the best part of an hour before they even know their instructions arrived. This is not a communication problem that better technology can fix. It is a property of distance and the fixed speed of light. Go further. Jupiter, the largest planet in the solar system, sits between about 33 and 52 light minutes away, depending on where it is in its orbit. Saturn is between 1 hour and 24 minutes. Uranus runs to 2 or 3 hours. Neptune, the outermost of the 8 planets, lies between about 4 and 5 light hours from Earth. A signal sent to a spacecraft orbiting Neptune would take between 4 and 5 hours to arrive, and another 4 to 5 hours for any reply to return. The simplest exchange with anything at Neptune takes the better part of a day, and Neptune is still, emphatically, inside the solar system. Beyond Neptune lies the Kuiper Belt, a disk of ice and rock extending from about 30 astronomical units out to perhaps 50 astronomical units from the Sun. An astronomical unit being the average distance between the Earth and the Sun, roughly 150 million kilometers. Beyond that lie less defined regions, the scattered disk, the inner Oort cloud, the outer Oort cloud, vast loosely structured shells of cometary material held by the Sun's gravity. The outer Oort cloud, in the most generous estimates, may extend 1 or even 2 light-years from the Sun. The Sun's domain is not a tight package of 8 planets. It is an enormous, diffuse sphere of gravitational influence, stretching perhaps 2 light-years in every direction. In 1977, humanity launched the farthest traveling object we have ever built. Voyager 1 left Earth on the 5th of September, 1977, carried outward past Jupiter and Saturn by the gravity of each planet in turn, then flung onto a trajectory that would take it beyond the reach of the solar system entirely. There was no plan to bring it back. It was not designed to return. It was designed to go and keep going, and transmit what it found for as long as its power held. As of early 2026, Voyager 1 is approximately 15.7 billion miles from Earth, roughly 168 astronomical units. A radio signal from the spacecraft, traveling at the speed of light, takes approximately 23 hours and 33 minutes to reach us. The engineers at NASA's Jet Propulsion Laboratory who manage the mission send a command and then wait nearly a full day for it to arrive. They wait another day for any acknowledgement to return. Every exchange takes 2 days. Think about what that means. Nearly 50 years of continuous travel at approximately 38,000 miles per hour. And still, 23 hours for a radio signal to cross the distance. Later in 2026, sometime around November by current projections, Voyager 1 will cross a threshold no human-made object has ever crossed. It will be exactly 1 light day from Earth. The distance light travels in 24 hours. That will be a first in the history of our species. Something we built, something we launched, reaching 1 light day from the planet it left. 50 years at 38,000 miles per hour to reach 1 light day. The nearest star to our Sun is Proxima Centauri, 4.2 light years away. Not 4.2 light days. Light years. A light year is 365 light days. At its current speed, Voyager 1 would take approximately 73,000 years to reach Proxima Centauri, and it is not heading in that direction. We have sent our fastest, farthest-reaching machine into space, flown it for nearly half a century, and it has traveled less than 2/1000ths of the distance to the nearest other star. We are not going anywhere anytime soon. The solar system alone defeats us. Now think about what it means for anyone trying to find us. Since the early decades of the 20th century, human civilization has been generating radio waves, signals that leak outward into space from broadcast towers, television transmitters, radar arrays, and communications infrastructure. Those signals travel at the speed of light in all directions, forming an expanding sphere of electromagnetic noise that any sufficiently sensitive receiver, anywhere in the universe, could in principle detect. That sphere now extends roughly 125 light-years from Earth in every direction. 125 light-years is our footprint, the total extent of any evidence of our technological existence, measured not by machines we have sent, but by the faint traces of our transmissions. And the Milky Way is 100,000 light-years across. Our signal bubble, placed inside the Milky Way, is roughly analogous to a tennis ball placed inside a football stadium. There are an estimated 250 billion stars in the Milky Way, and our earliest signals have reached the neighborhood of perhaps a few thousand of them. Most of the galaxy has heard nothing from us. If you were standing in the far reaches of our own galaxy tonight, listening with the most sensitive instruments imaginable for any sign of life on a distant world, the Earth would be completely silent. Our transmissions would not have arrived yet, and will not for thousands of years. We have been broadcasting for barely a century. The Milky Way is 100,000 light-years wide. The signal has covered roughly 0.1% of that distance. We are, in every meaningful sense, invisible. This was not always how large people understood the universe to be. In April of 1920, two astronomers stood before the National Academy of Sciences in Washington to debate a question that seemed, at the time, genuinely open. Harlow Shapley, one of the most respected observational astronomers of his generation, argued that the Milky Way was effectively the whole of the universe, that the faint spiral nebulae visible through large telescopes were clouds of gas and dust within our own galaxy, and that there was nothing beyond it worth naming. Heber Curtis, his opponent, argued the opposite, that the spirals were separate systems, separate island universes, each containing billions of stars, lying at distances that dwarfed anything previously imagined. It was called the Great Debate, and the evidence at the time was genuinely ambiguous. 4 years later, Edwin Hubble settled it. Working at the Mount Wilson Observatory in California in 1924, Hubble used a type of variable star, a star that brightens and dims on a predictable cycle that reveals its true luminosity, to measure the distance to the Andromeda Nebula, the large, faint smudge visible on dark autumn nights. He found it lay at an enormous distance, well outside any possible boundary for the Milky Way. We now know the true figure is 2.5 million light-years, but even Hubble's original estimate was conclusive. The Andromeda Nebula was not a cloud inside the Milky Way. It was a separate galaxy, another vast system of stars, another island in an ocean of islands. The ocean, it turned out, had barely been glimpsed. The Milky Way itself, as we now understand it, is roughly 100,000 light-years in diameter. At its center sits a supermassive black hole, a region of collapsed space-time with a mass approximately 4 million times that of our Sun, designated Sagittarius A star. Our Sun sits out in a minor spiral arm called the Orion Arm, about 26,000 light-years from the galactic center, orbiting the galaxy at roughly 830,000 kilometers per hour. At that speed, completing a single orbit of the Milky Way takes the Sun approximately 230 million years. The last time the Sun was at the same position in its galactic orbit, the dominant land animals on Earth were the earliest dinosaurs. 230 million years for one trip around our own galaxy. If you could somehow compress the entire history of the Milky Way into a single calendar year, with the galaxy's formation at the 1st of January and today at midnight on the 31st of December, the Sun would not have formed until early September. Life on Earth would not appear until October. The dinosaurs would exist for about 4 days in late December. All of human history, from the first stone tools to the present moment, would occupy the final 18 seconds of the year. Everything we have ever done, everyone who has ever lived, every civilization that ever rose and fell, every instrument we have ever pointed at the sky. 18 seconds in the life of one galaxy out of 2 trillion. There are 2 trillion galaxies in the observable universe. The universe is not just big, it is mostly nothing. Vast stretches of space containing no stars, no light, no structure of any detectable kind. Only emptiness so profound and so persistent that it dwarfs everything that exists within it. And what matter there is, has organized itself into a pattern that took cosmologists decades to map and still longer to explain. A pattern shaped not by what is present, but by the geometry of what is absent. That pattern begins with voids so enormous they should not be possible. In 1981, a team of astronomers at the University of Michigan set out to map a patch of the sky in 3 dimensions. Robert Kirshner and his colleagues were conducting a redshift survey, measuring the rate at which galaxies are moving away from us, which, because of the expanding universe, reveals how far away they are. Point a telescope at a region of sky, record the redshifts of every galaxy you can find, and you build a 3-dimensional picture of where matter is distributed. It was methodical, careful work, the kind of survey that usually produces a smooth and predictable map. In 3 separate fields of sky, all separated from each other by about 35 degrees, the team found almost no galaxies at all. Where their predictions said there should have been dozens of galaxies, where a uniform distribution of matter would have put perhaps 30 or more, there was a single galaxy in one field and nothing in the others. Kirshner and his colleagues checked their instruments, they checked their data reduction, they checked their methodology. Everything was correct. There simply were not galaxies there. The space in that region of the sky was, for all practical purposes, empty. What they had stumbled into is now called the Boötes Void, after the constellation in whose direction it lies. It is one of the most unsettling structures in the known universe. The Boötes Void is roughly spherical, and it is enormous. Its diameter is approximately 330 million light-years. Its center lies about 700 million light-years from Earth. Inside this vast sphere of space, where the average density of the universe would lead you to expect roughly 2,000 galaxies, astronomers have found 60 galaxies in a region that should hold 2,000. That is a density of about 3% of normal. The void is not empty in the absolute sense. Nothing in the universe is truly empty, but it is as close to empty as large-scale structures get. To appreciate what 330 million light-years means, compare it to something familiar. The Milky Way galaxy is 100,000 light-years across. The Boötes Void is 3,300 times wider than the Milky Way. If you set off from one edge of the Boötes Void traveling at the speed of light, the fastest speed physically possible, you would travel for 330 million years before reaching the other side. 330 million years ago, the dominant animals on Earth were early reptiles. Dinosaurs had not yet appeared. The continents were still assembled into the supercontinent of Pangaea. You would cross that entire span of time, every year of it, every extinction event and evolutionary leap and continental shift, and emerge from the void to find the universe still going. In the 1980s and 1990s, a series of surveys sent astronomers into the Boötes Void looking for anything that might be hiding there. One of the most persistent of those searchers was Greg Aldering, who spent years hunting for galaxies within its boundaries. He and his colleagues eventually catalogued 60 galaxies within the void, a painstaking effort that confirmed just how profoundly underdense the region is. In the course of that work, Aldering made an observation that has stayed with cosmologists ever since. He noted that if the Milky Way happened to be located at the center of the Boötes Void, rather than where it actually sits, we would not have discovered that other galaxies existed until the 1960s. Think about that for a moment. The realization that the universe contains other galaxies, billions of them, each holding hundreds of billions of stars, was one of the great intellectual watersheds of the 20th century. Edwin Hubble's measurement of the distance to Andromeda in 1924 shattered the assumption that the Milky Way was all there was. It transformed our understanding of what the universe is and how large it might be. That realization, which has shaped everything that came after in cosmology, would have been delayed by decades if our galaxy happened to be sitting somewhere else. The nearest galaxy to the edge of a void that size would simply not have been visible to early optical telescopes. We would have looked out into what appeared to be an empty universe and concluded we were alone, not because we were, but because the architecture around us would have hidden the evidence. You could have been born into a version of human history in which the entire discipline of extragalactic astronomy simply did not exist yet. Not because the universe would have been different, but because you would have been sitting in the wrong place. The Boötes Void was initially treated as a curiosity, an anomaly, an outlier, the kind of thing that shows up occasionally at the edges of a distribution and does not say much about the center. But as surveys improved and the mapping of large-scale structure became more sophisticated, something harder to dismiss emerged. Voids are not anomalies, they are the rule. Roughly 80% of the volume of the observable universe is void. Not 80% of the universe's mass. The mass is concentrated into the remaining 20%. which is where the galaxies and clusters are. But in terms of sheer volume, in terms of what the universe is mostly made of when you look at the whole thing, it is emptiness. Vast, structured emptiness, shaped by gravity and dark energy over billions of years. The galaxies, for all their grandeur, are a thin skin of luminous matter stretched over a skeleton of absence. This is counterintuitive in a way that is difficult to entirely absorb. We think of space as the backdrop and matter as the substance. But at the largest scales, the substance is rare and the emptiness is primary. The universe is not a sea with islands, it is a foam. Thin walls and filaments of matter enclosing enormous volumes of almost nothing, the way soap bubbles enclose pockets of air. Now consider where we are inside that foam. In 2013, 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, published evidence for an underdense region of space surrounding our own galaxy, a structure so large it dwarfs even the Boötes void. The structure has come to be known by their initials, the KBC void, sometimes called the local hole. Its proposed diameter is approximately 2 billion light-years. It contains the Milky Way, the local group of galaxies, and most of the enormous Laniakea supercluster. By their measurement, the region we inhabit is approximately 20% less dense than the cosmic average, meaning that within a bubble, roughly 2 billion light-years across, there is significantly less matter than you would expect to find in a comparable region elsewhere in the universe. The KBC void is still somewhat contested. Not all analyses of the galaxy distribution agree on its precise extent, and some estimates are more conservative than others. But the broad finding that we appear to sit within an underdense region of cosmic real estate has proven resilient to scrutiny. And it has an interesting consequence. Galaxies inside a void do not simply float in place. They are gravitationally attracted to the denser walls that surround the void, the filaments and clusters on its edges, where matter has accumulated over billions of years. Galaxies near the center of a void get tugged slowly outward, toward the denser boundary. And this creates an effect that matters for the Hubble tension. If the Milky Way and its neighbors are sitting inside a large underdense bubble, then the galaxies we use to measure the local expansion rate of the universe are not a representative sample of the universe as a whole. They are slightly accelerated, nudged outward by the gravitational pull of the denser walls around the void. This would make the local expansion rate appear faster than the global rate. It would not explain the entire discrepancy between the two Hubble constant measurements. The void would need to be extraordinarily large and the density contrast unusually strong to account for the full 9% gap, but it might account for part of it. We may be measuring the universe from the bottom of a cosmic pothole and mistaking the slope for flat ground. The voids themselves have a history that reaches back to the very first instant of time. In the first tiny fraction of a second after the Big Bang, the universe was not uniform. Quantum mechanics, which governs the behavior of matter at the smallest scales, ensures that nothing is ever perfectly smooth. There are always fluctuations, tiny, random variations in energy density, smaller than any scale we can directly observe, inherent in the fabric of space itself. In the enormously rapid expansion that followed, the period cosmologists call inflation, those microscopic fluctuations were stretched to cosmic scale. Regions that were infinitesimally denser than average became the seeds of future galaxy clusters. Regions that were infinitesimally less dense became the seeds of voids. The Boötes void, in other words, traces its origin to a quantum fluctuation smaller than a proton, occurring in the first moments of existence, that was then inflated to a sphere 330 million light-years across over 13.8 billion years of cosmic evolution. The universe, at its largest scales, is shaped by the smallest possible events. And the dominant feature of that universe, the thing that accounts for most of its volume, that determines where galaxies form and how light travels and where civilizations might or might not emerge, is not matter. It is the absence of matter. The cosmic web is shaped more by what is missing than by what is there. The universe's skeleton is not its stars. It is the voids between them. And that skeleton has a structure, a vast, intricate, three-dimensional architecture that we are only now beginning to map with the precision it deserves. If 80% of the universe is void, what fills the 20% that remains? The answer is a structure so vast, so recently confirmed by direct observation for the first time, that cosmologists are still absorbing what it means to have finally seen it. The matter in the universe is not scattered at random. If you could take every galaxy in the observable universe and plot each one's position in 3 dimensions, you would not see a uniform fog. You would see something that looks, at first glance, almost biological. A vast, intricate network of filaments and sheets, stretching across hundreds of millions of light years, branching and converging, intersecting at dense nodes where the brightest galaxy clusters accumulate, and enclosing those filaments, taking up most of the volume, the enormous empty voids we have just been describing. This is the cosmic web. It is the largest coherent structure that exists. And until recently, no one had ever directly photographed a single strand of it. The existence of the web was predicted long before it was seen. In the 1980s, as computational power grew and cosmologists began running simulations of how the universe evolves under gravity, the same pattern kept appearing. Feed the simulation the correct starting conditions, the slight variations in matter density inherited from the early universe, the properties of gravity, the behavior of dark matter, and the matter in the simulation spontaneously organizes itself over billions of simulated years into precisely this architecture. Threads and sheets where matter is dense, empty bubbles where it is sparse, a foam spanning the entire simulated universe from edge to edge. The simulations were so consistent that cosmologists spent decades treating the web as established fact, confident it was real, even as direct high-resolution observational confirmation remained beyond their instruments. The difficulty is physical. The cosmic web is composed primarily of diffuse hydrogen, spread thinly across the vast spaces between galaxies. Hydrogen gas emits light at specific wavelengths as electrons within it transition between energy levels. But when that gas is dispersed across millions of light years at filament densities, the emission barely rises above the natural background glow of the sky. To see a filament directly, you need 3 things simultaneously: an instrument of genuine sensitivity, capable of isolating that faint hydrogen emission against background noise, a favorable geometry, some natural illumination from the universe itself that brightens the target above the threshold of detection, and an observing program willing to commit a remarkable amount of telescope time to a single small region of sky. In January of 2025, all 3 conditions came together. Davide Tornotti, a doctoral student at the University of Milano Bicocca in Italy, led an international research collaboration that included scientists from the Max Planck Institute for Astrophysics in Germany. Their target was a specific patch of sky where 2 distant galaxies appear close together as seen from Earth. Each of these galaxies harbors a supermassive black hole at its center, actively consuming surrounding gas and converting that consumption into a ferocious outpouring of radiation that makes the galactic core visible across billions of light years. Objects of this type are called quasars. The 2 quasars in this region were separated by a distance small enough on the sky that the light they poured into the space between them could illuminate the filament of gas connecting them, making visible, like dust caught in a shaft of sunlight, a structure that would otherwise be too faint to detect. The instrument was called MUSE, the Multi-Unit Spectroscopic Explorer, mounted on the Very Large Telescope at the European Southern Observatory in the Atacama Desert of Chile. MUSE is not a conventional camera. It is a spectrograph of unusual design that records the complete spectrum of light from every point in its field of view simultaneously, allowing it to detect the faint hydrogen emission at specific wavelengths while mapping the velocity of that gas across the entire field at the same time. For detecting a cosmic filament, this matters enormously. The emission appears at a predictable wavelength, Muse can isolate it and map it across the field, separating signal from noise in a way that simpler instruments cannot. The team accumulated more than 100 hours of observing time on this single region of sky, gathering data across multiple seasons, building up the signal until it was strong enough to analyze with confidence. 100 hours on a single patch of sky, waiting for photons that had been traveling for 11 billion years to accumulate in sufficient numbers to be mapped. On January the 29th, 2025, they published their findings in the journal Nature Astronomy. What they had captured was a filament of hydrogen gas stretching across 3 million light-years of space, bridging the two quasar-host galaxies. 3 million light-years, roughly the distance between the Milky Way and the Andromeda Galaxy. The light from that gas had been in transit for 11 billion years before it reached the telescope in Chile. The universe was less than 3 billion years old when those photons began their journey. We are seeing the filament as it existed during the era when the cosmos was building galaxies at the highest rate it has ever managed, drawing on the raw material of structures like this one to fuel an epoch of star formation that has never been equaled since. The image was not a blurred smear of uniform brightness. The filament had internal structure, clumps of denser gas, brighter regions, variations in emission along its length that spoke to the actual physical complexity of the object. When the team overlaid their observation on supercomputer simulations of what such a filament should look like under those conditions, the agreement was striking. The shape, the density variations, the spatial distribution of emission, the simulation had predicted all of it. The cosmic web had been confirmed in direct high-resolution observation. For the first time, a structure that had existed only in theory and in indirect inference could be seen and compared to predictions pixel by pixel. The predictions were right. Beyond the confirmation of the web's existence, the observations have revealed that filaments are more dynamic than the simplest models anticipated. Work by several research groups, using the motions of galaxies within and around filaments, has found that filaments rotate. Galaxies connected by a filament tend to share a common sense of angular momentum. They spin in correlated directions, as if the filament has been channeling and transmitting rotation across millions of light-years during the process of galaxy formation. This was not predicted by the earliest models of the web. It suggests that filaments are not passive conduits, but active participants in the dynamics of the galaxies they connect, shaping not only where those galaxies form, but how they move and spin. The evidence of filament rotation also points towards something the direct image cannot show. The angular momentum carried by a rotating filament has to come from somewhere. Current models suggest it originates in the large-scale tidal forces generated by the surrounding matter distribution, the gravitational influence of nearby clusters and voids imprinting a slow twist on gas as it flows inward along dark matter threads. This is a subtle, long-range effect operating across tens of millions of light-years, and it leaves a permanent mark on every galaxy that forms within the filament. The direction a galaxy spins, the tilt of its disk, the orientation of its rotation axis. None of these are arbitrary. They are the accumulated consequence of forces that acted on the gas before that galaxy existed. Forces that originated in the architecture of the web, which in turn originated in quantum fluctuations stretched to cosmic scale in the first fraction of a second of time. There is a causal line connecting the rotation of a galaxy, visible through a telescope today, to a quantum event that occurred before any matter in that galaxy was assembled. The filaments carry that history forward. They are not merely conduits of matter. They are conduits of information about the very beginning of everything. The filament is also, in a very direct sense, a supply line. The gas flowing along it was moving toward the denser regions at each end, where it would accumulate, cool, and eventually collapse under gravity into new stars. The cosmic web is the plumbing of the universe. Every galaxy we have ever observed was built, at least in part, by matter flowing along structures like the one Tornotti's team imaged. The raw material for stars, and eventually for planets, for chemistry, for everything built from atoms, was delivered along threads of gas that extend for millions of light years through space. The discovery that this delivery mechanism could be directly observed and that its observed properties matched theoretical predictions so closely was a significant moment in the history of cosmology. It meant that the simulations were not merely producing plausible-looking universes that superficially resembled reality at large scales. They were producing the correct internal structure of individual filaments at the level of detail that only direct high-resolution imaging can test. The standard model of cosmology, for all the pressure it is currently under in other respects, appears to be getting the Webb right. That is useful to know. It is also, given the other anomalies piling up around it, a little unsettling. A model can be right about the architecture and still be wrong about the contents. Now consider what is actually holding those threads in place. The gas in the filament is ordinary matter, hydrogen atoms, visible because they emit light at specific wavelengths. But hydrogen does not accumulate into cosmic scale filaments on its own. It follows gravity. It falls into whatever gravitational structure the universe has created for it over billions of years. And the gravitational structure that produces the Webb, the invisible channels along which gas flows from empty voids toward dense intersections, is not made of ordinary matter at all. Dark matter forms the Webb's skeleton. In the early universe, long before the first stars formed, dark matter began to clump under its own gravity. Tiny fluctuations in dark matter density grew, pulling in more dark matter, assembling over billions of years into an intricate three-dimensional scaffolding, whose shape was determined by the pattern of quantum fluctuations that inflations stretch to cosmic scale in the first fraction of a second. Ordinary matter, the atoms, the gas, the eventual galaxies, fell into the gravitational wells dark matter had already carved. The gas settled along the dark matter threads. The galaxies condensed at the intersections. Without the Webb, there would be no galaxies. Without dark matter, there would be no Webb. What Tornotti and his colleagues spent 100 hours imaging in Chile was the visible shadow of an invisible architecture. Ordinary hydrogen atoms tracing the contours of something we have never directly detected in any laboratory on Earth. The frame is built from darkness, and that darkness is not a minor correction to our picture of the universe. It is the universe's dominant component, 5%. That is the fraction. Everything you have ever seen, every star in every sky you have looked at, every planet that has ever been photographed, every atom in every element on the periodic table, every photon of light that has reached your eyes, or your instruments, or your telescopes since the beginning of scientific observation. All of it, the entirety of ordinary matter in the universe, adds up to 5% of what the universe actually contains. The other 95% is something else, and we do not fully understand what. This is not a provisional estimate awaiting refinement. It is the considered conclusion of the most precise measurements cosmologists have ever made, confirmed by multiple independent lines of evidence across decades of observation. The universe is made mostly of things we have never directly detected in any laboratory, interacting through mechanisms we have not been able to isolate, forming structures we can only map by their gravitational influence on the 5% we can see. It is, to put it plainly, a stunning situation for a civilization that prides itself on scientific understanding. The first person to notice that something was wrong was a Swiss astrophysicist named Fritz Zwicky, working at the California Institute of Technology in the early 1930s. Zwicky was studying the Coma Cluster, a dense collection of hundreds of galaxies lying about 320 million light-years from Earth, one of the largest galaxy clusters in the relatively local universe. To understand how a galaxy cluster behaves, you need to know how fast its individual galaxies are moving. Zwicky measured those velocities by analyzing the Doppler shift of their light, the same principle that makes a siren sound higher as it approaches and lower as it recedes, applied to the stretching and compressing of light waves from moving objects. What he found troubled him. The galaxies in the Coma Cluster were moving so fast that, if the only mass present were the mass visible in the luminous galaxies themselves, the cluster should have flown apart long ago. The visible matter provided nowhere near enough gravitational force to hold the system together. Zwicky concluded that the cluster must contain a large amount of mass that could not be seen. He called it Dunkel Materie, dark matter. His colleagues were largely unpersuaded. The idea sat at the margins of astrophysics for the better part of 4 decades. Then, in the late 1960s, a young astronomer named Vera Rubin arrived at the Department of Terrestrial Magnetism at the Carnegie Institution in Washington and asked for a job. She had been looking for interesting problems to work on, problems that would not provoke controversy, problems where the data could speak for itself. She had been advised to study the rotation of galaxies, how fast the stars in a spiral galaxy move around the galactic center. It seemed, at the time, like a straightforward question with an expected answer. Rubin began working with an instrument specialist named Kent Ford, who had built an unusually sensitive spectrograph capable of measuring stellar velocities with a precision not previously achievable. Together, they pointed it at the Andromeda Galaxy, the nearest large spiral galaxy to our own. They measured the velocities of stars at different distances from Andromeda's center, plotting the results as what astronomers call a rotation curve, a graph showing how orbital speed changes with distance from the core. The expectation, based on Newtonian gravity applied to the visible mass distribution, was clear. In our own solar system, the outer planets move more slowly than the inner ones. Mercury, closest to the Sun, moves the fastest. Neptune, at the outer edge, moves the slowest. This is because almost all the mass in the solar system is concentrated in the Sun, and gravitational force weakens with distance. The same should apply to a galaxy. The stars near the bright, dense center should orbit fastest, and the stars at the outer edges, far from the concentrated mass of the core, should orbit more slowly. The rotation curve should slope downward. Rubin and Ford published their first results in February 1970. The rotation curve was flat. The stars in the outer reaches of Andromeda were moving just as fast as the stars near the center. At every distance from the core, the orbital velocity was roughly the same. This should have been impossible given the visible mass distribution. There was not enough luminous matter to explain it. The only way to make sense of a flat rotation curve is to postulate that there is mass in the outer parts of the galaxy. Mass that is not shining. Mass that does not interact with light in any way we can detect, extending far beyond the visible disk of stars. A halo of invisible matter, encompassing the galaxy and providing the gravitational force that keeps the outer stars orbiting at their unexpected speed. Rubin and Ford did not immediately claim they had discovered dark matter. They were cautious, and the scientific community was skeptical. But Rubin understood what the data was saying. She returned to the telescopes and began systematically measuring the rotation curves of other spiral galaxies, one by one. The work continued from 1976 through to the late 1980s. Each new galaxy produced the same result: flat curves, everywhere, without exception. By the early 1980s, the evidence had accumulated beyond reasonable dispute. Galaxies are embedded in halos of dark matter that are many times more massive than the visible stars and gas they contain. The luminous part of a galaxy, the part we see, is a small fraction of what is actually there. Rubin's calculations suggested that galaxies contain at least 5 to 10 times more mass than their stars account for. Zwicky had been right. He had simply been right 40 years too early. The current best estimate, derived from the cosmic microwave background, large-scale structure surveys, and gravitational lensing studies that map how matter bends light passing around galaxy clusters, is that dark matter accounts for approximately 27% of the total energy mass content of the universe. It is 5 times more abundant than ordinary matter. It was present from the very beginning. It built the web. It surrounds every galaxy like an invisible scaffolding. And nobody has ever detected a dark matter particle in a laboratory. Vera Rubin died on December 25, 2016, at the age of 88. She never received the Nobel Prize, a fact that many of her colleagues considered a serious omission. but her legacy is now embodied in concrete and steel. In 2019, the Large Synoptic Survey Telescope on the mountain of Cerro Pachon in Chile was renamed the Vera C. Rubin Observatory in her honor, the first major national observatory in the United States to bear the name of a woman. In April of 2025, it began operations. Its purpose is to conduct a 10-year survey of the entire southern sky, photographing it every few nights, building a time-lapse map of the universe at a scale and depth no previous instrument has achieved. One of its primary scientific goals is to map dark matter, to trace the gravitational distortions it produces in the shapes of billions of background galaxies, and from those distortions, reconstruct where the dark matter is and how it is distributed across the cosmos. The woman whose observations first proved that dark matter exists now has the most powerful dark matter survey telescope ever built, conducting that work in her name. But dark matter is not the end of the accounting. In 1998, two independent teams of astronomers, one led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rees, working primarily with Australian and American colleagues, were studying the brightness of distant Type I as supernovae. These exploding stars flare with a predictable luminosity, making them useful as distance markers. Both teams were using supernovae to measure how the expansion of the universe had changed over time, expecting to find that gravity was gradually slowing it down. The further back in time you look, the more distant the supernova, the faster the universe should have been expanding in the past, with the expansion rate declining toward the present as gravity did its work. That was the expectation. The data showed the opposite. The expansion is not slowing down, it is accelerating. Something is pushing space apart at an increasing rate, overcoming the gravitational attraction of all the matter in the universe. This something has been named dark energy, and it is the dominant component of the universe. The best current estimate is that dark energy constitutes approximately 68% of everything. Ordinary matter is 5%. Dark matter is 27%. Everything we have ever detected, every element in the periodic table, every photon, every neutrino, every atom in every star in every galaxy, in every image ever taken by every telescope ever pointed at the sky, that is the 5%. The nature of dark energy is almost entirely unknown. It behaves mathematically like a property of space itself, a constant energy density that pervades every point in the universe equally, causing space to expand and accelerating that expansion over time. Einstein included something like it in his equations of general relativity more than a century ago, calling it a cosmological constant, then famously removed it, calling it his greatest blunder. The 1998 discovery suggests it may have been his greatest insight. And dark energy has a consequence that goes beyond mere acceleration. It imposes a hard limit on what we will ever be able to communicate with, influence, or observe. The observable universe currently spans 93 billion light-years, but not all of that is still accessible to us. Because of dark energy's acceleration, any galaxy that is currently receding from us at a speed faster than light is already, in a physical sense, gone. No signal we emit today will ever catch it, no matter how long we wait. That boundary, the cosmic event horizon, currently lies at approximately 16 billion light-years from Earth. Any galaxy beyond that distance is already permanently out of reach. The light we can see from those galaxies now was emitted long ago, before they crossed the horizon. We can see them. We cannot touch them. We cannot signal them. They have, in the only meaningful physical sense, already left the universe we can participate in. Most of the galaxies in the observable universe are already beyond the cosmic event horizon. We can see a universe far larger than the universe we can still interact with. And as dark energy continues to accelerate the expansion of space, more and more galaxies will cross that horizon, receding beyond any possible contact. The observable universe we see now is the largest it will ever be from our perspective. From here, it only shrinks. We are discovering, one measurement at a time, that what we can see is not what is there, and that what is there is mostly something we do not understand. 95% of the universe is invisible to us, indetectable by any instrument we have built, unexplained by any theory we have fully worked out. Dark energy is pushing everything apart, but something much closer to home is also pulling. The Milky Way is not sitting still in all this expansion. It is moving, being dragged at extraordinary speed towards something so massive and so hidden that for decades we could not even establish what it was. The Milky Way is not sitting still. This is easy to overlook. When you look up at the night sky, the stars appear fixed, ancient points of light that have occupied the same positions since before any human drew a map of them. The sky feels static, permanent, a reliable backdrop against which everything else in life changes. But the galaxy you are standing inside is moving through space at an extraordinary speed, being pulled by something enormous. And for most of the 20th century, nobody could agree on what that something was. In the 1970s and 80s, a series of observations revealed something deeply unsettling about the motion of the galaxies in our neighborhood. Astronomers studying the velocities of galaxies in the local universe, the Milky Way, the Andromeda Galaxy, the dozens of smaller galaxies bound together in what is called the local group, and hundreds of other galaxies beyond it, found that all of them were moving in the same direction. Not simply moving apart from each other, which would be expected in an expanding universe. Moving together, as a group, in a coordinated flow, toward a point in the sky located in the direction of the constellations Centaurus and Norma. Something in that direction was pulling everything in the local universe toward it. The problem was that the region they were pointing toward was obscured. The plane of our own galaxy, the dense disk of stars, gas, and dust that forms the Milky Way, runs across the sky in a band of concentrated light. And behind that band, there is a zone of avoidance, a region so cluttered with the infrared radiation and dust of the Milky Way itself that optical telescopes cannot see through it to whatever lies on the other side. The gravitational source was hidden behind our own galaxy. Astronomers named it the Great Attractor and spent years trying to determine what it was. When they finally penetrated the zone of avoidance, using radio telescopes and later infrared surveys that could see through the dust, they found something significant but not sufficient. There were large galaxy clusters in that region, particularly a dense concentration called the Norma cluster. But their combined mass was not enough to fully account for the flow. Something beyond them was also contributing, and the full picture of what was pulling the Milky Way and its neighbors would not be clear until a very different kind of observation was brought to bear. The conceptual breakthrough came from R. Brent Tully at the University of Hawaii, working with colleagues Hélène Courtois, Yehuda Hoffman, and Daniel Pomered. The key, Tully's team realized, was not to map where galaxies are located. Plenty of surveys had done that. The key was to map where galaxies are going. Every galaxy in the universe has what cosmologists call a peculiar velocity, a motion above and beyond what you would expect simply from the overall expansion of space. The expansion of the universe carries all galaxies apart from all others as space stretches, but each galaxy also has a local motion, determined by the gravitational landscape around it. A galaxy being pulled toward a concentration of mass will be moving faster than the expansion alone would predict. A galaxy sitting in a region of low density will be lagging slightly behind the expansion, being tugged outward toward denser surroundings. These peculiar velocities are tiny, often just a few hundred kilometers per second against the backdrop of cosmic distances. But they are measurable, and they encode information that pure positional maps do not contain. They reveal not just the distribution of matter, but the flow of matter. They are a map not of where things are, but of where gravity is pulling them. Tully's team assembled a catalogue of peculiar velocities for more than 8,000 galaxies within several hundred million light-years of the Milky Way. Then they looked for the underlying structure. They were searching for gravitational basins, regions where all the galaxy flows converge inward, draining toward a common gravitational center the way water drains toward the low point of a watershed. Within a single drainage basin, all the water on a hillside flows to the same river, regardless of how far apart the water droplets started. The boundaries between basins, the ridgelines where water can flow either way, are sharp and definable. On September 4th, 2014, Tully and his colleagues published their results in the journal Nature. The structure they had mapped was a supercluster, a gravitational basin containing the Milky Way, the Local Group, the Virgo cluster, and dozens of other galaxy clusters and filaments, all flowing toward the same central attractor. They named it Laniakea, from the Hawaiian words for immense heaven, a name suggested by a Hawaiian language professor at the request of the research team, in recognition of the Polynesian navigators who used the stars to cross the Pacific Ocean and whose legacy of reading the sky now felt newly resonant. Laniakea is enormous. It spans approximately 500 million light-years in diameter. It contains an estimated 100,000 large galaxies. Its total mass is equivalent to roughly 10 to the power of 17 solar masses. That is 100 quadrillion times the mass of the Sun, or about 100,000 times the mass of the Milky Way itself. It is one of the largest structures in the known universe, and the Milky Way sits at its outermost edge, not at the center, near the gravitational focus where all the flow lines converge. At the far periphery, near the boundary with neighboring superclusters. The Great Attractor, which drew so much attention for so many years, turned out to be not a single object, but the deep central valley of Laniakea, the gravitational nadir toward which the entire supercluster is slowly, collectively draining. The Milky Way is a drop of water on a hillside, and the hillside is 500 million light-years wide. The motion is real, and it is fast. Our galaxy and its neighbors are flowing toward the Laniakea attractor at roughly 600 kilometers per second. To put that in human terms, 600 kilometers per second is roughly 2 million kilometers per hour, fast enough to cross the diameter of the Earth in under 2 minutes. And yet this is not a collision course, not a catastrophe. It is simply the ordinary gravitational choreography of a universe where matter is unevenly distributed and everything is falling, slowly and perpetually, toward the nearest gravitational concentration. In the context of Laniakea's dimensions, at 600 kilometers per second, the journey toward the attractor would take trillions of years. There is, however, a reason we will never arrive. Dark energy is working against it. The same accelerating expansion that is pushing distant galaxies over the cosmic event horizon is also pushing the walls of Laniakea apart. Gravity pulls inward at the local scale. Dark energy expands space at the cosmic scale. And the two forces are in a slow, ongoing contest whose outcome depends on distance. At large enough scales, dark energy wins. The Shapley supercluster, a vast concentration of galaxies lying approximately 650 million light-years away, beyond the edge of Laniakea, exerts its own gravitational pull on our supercluster as a whole. There is evidence that Laniakea itself is part of an even larger structure, the Pisces-Cetus supercluster complex, stretching over 1 billion light-years. But at those distances, dark energy is overtaking gravity. The farther you look, the faster everything is receding. If you launch the fastest possible spacecraft toward the gravitational center of Laniakea and pointed it in the direction of the Great Attractor, dark energy would ensure that the space between you and your destination expanded faster than you could cross it. The destination would recede as you traveled. You would never arrive, not because of any limitation in your engines, but because the universe is structured in such a way that the destination is permanently getting further away. This is not a failure of technology. It is not a problem that a better rocket could solve. It is a property of the physics of space itself, working at scales where human intuitions about travel and distance stop being useful. The Milky Way is caught between opposing forces, gravity pulling toward the attractor at the heart of Laniakea, dark energy pushing the larger structure apart. It is, in the longest possible view, a losing battle for gravity, as dark energy grows ever more dominant with the expansion of space. But on timescales shorter than the lifetime of stars, the flow continues. Your cosmic address starts here, On a small rocky planet, orbiting a yellow star in a minor spiral arm of a middling galaxy, on the outer rim of a supercluster 500 million light-years across, being simultaneously pulled toward a gravitational center it will never reach and pushed away from the rest of the universe by a force it cannot resist. Let us write that address out, line by line, from the beginning. Because when you see it whole, when you read all the layers together, it is the most humbling document in the history of human thought. Every person on Earth has an address. Most addresses have 5 or 6 lines: a name, a street, a city, a country, a postcode. They are designed to locate you within the human world, to distinguish you from every other person in every other place, to give the postal system and the navigation software a precise coordinate to work from. Your real address is longer than that. It has more lines, and each line is larger than the one before it, by a factor that does not just shrink the line above it, it makes it disappear. The way a city block disappears when you zoom out to see a continent. The way a continent disappears when you pull back to see the full curve of the Earth from orbit. Except that the steps we are about to take are not from block to continent to planet. They are from planet to solar system to galaxy to supercluster to observable universe. And each jump is not a factor of hundreds or thousands, but a factor of millions or billions or more. Let us write the address out, layer by layer, from the beginning. You are on Earth. The third planet orbiting a star we call the Sun, formed approximately 4.6 billion years ago from a collapsing cloud of gas and dust in the outer reaches of a young galaxy. Earth has a diameter of 12,742 kilometers. It is the largest of the 4 rocky inner planets. It has liquid water on its surface, a nitrogen-oxygen atmosphere, a magnetic field that deflects lethal solar radiation, and a geological history complicated enough to have produced, after 4 billion years of chemistry and evolution, beings capable of writing and reading this sentence. Every living thing we have ever discovered, every species named, every ecosystem documented, every fossil pulled from every cliff face, all of it exists here, on this single world. Above that line comes the solar system. Earth orbits the Sun at a mean distance of approximately 150 million kilometers, the unit used so often in planetary science that it has been given its own name, the astronomical unit. Mars orbits at about 1.5 astronomical units, Jupiter at 5.2, Saturn at 9.5, Uranus at 19, Neptune, the outermost of the 8 major planets, at approximately 30. The full width of the planetary system, measured across Neptune's orbit, is roughly 60 astronomical units. Light crosses it in about 8 hours. 8 hours to cross the entire span of the planetary architecture that contains everything humanity has ever directly visited or observed up close. But the solar system does not end at Neptune. The planetary system is surrounded by the Kuiper Belt, a ring of icy bodies extending from Neptune's orbit out to about 50 astronomical units. Beyond that, more diffuse and more distant, lies the Oort cloud, a vast, roughly spherical shell of perhaps hundreds of billions of icy objects, remnants of the formation of the solar system that were flung outward by gravitational interactions with the giant planets over billions of years. The Oort cloud has never been directly observed. Its existence is inferred from the trajectories of long-period comets, which arrive at the inner solar system from every direction in the sky, as if scattered from a shell surrounding the entire system at enormous distances. The outer edge of the Oort cloud may lie as far as 1 full light-year from the Sun. Voyager 1, launched in 1977 and traveling now for nearly 50 years at 38,000 miles per hour, has not yet reached it. That probe will need approximately 300 years to arrive at the inner Oort cloud, and perhaps 30,000 years to pass all the way through. The Oort cloud is the outermost boundary of the Sun's gravitational domain. Only beyond it does interstellar space begin in any meaningful sense. Above the solar system comes the Milky Way. Our Sun is one of an estimated 250 billion stars in a barred spiral galaxy approximately 100,000 light-years in diameter. The galaxy is structured as a central bulge of older, redder stars surrounded by a flattened disk of younger stars, gas, dust, and the spiral arm features that give it its characteristic shape when seen from outside. The Sun occupies a position in a relatively modest spur of one of those spiral arms, a structure called the Orion Arm, at a distance of approximately 26,000 light-years from the galactic center. We are not in the crowded interior, where stellar density is high, and the chances of disruptive gravitational encounters are greater. We are in the quieter suburbs of the galaxy, orbiting the center once every 230 million years. At the core of the Milky Way, 26,000 light-years from us, sits a supermassive black hole with a mass approximately 4 million times that of the Sun. It is called Sagittarius A star. At optical wavelengths, it is completely hidden behind the dust and gas of the galactic plane, but astronomers using infrared telescopes, whose longer wavelengths pass through the obscuring material as radio waves pass through fog, have spent decades tracking the individual orbits of stars in its immediate neighborhood. Those orbits are startling. Some stars complete a single orbit around Sagittarius A star in fewer than 20 years, swinging around something they cannot see at speeds of several thousand kilometers per second. The only explanation that fits is a mass of 4 million suns packed into a region smaller than our solar system. The nearest large galaxy is Andromeda, 2.5 million light-years away, visible on a dark night as a faint, elongated smudge, the most distant thing most people will ever see without optical aid. Andromeda is slightly more massive than the Milky Way. In approximately 4.5 billion years, the gravitational attraction between our two galaxies, already measurable in our approach velocity, will bring them into collision and eventual merger. It will not be a clean collision. The two systems will pass through each other, separate, return, and slowly coalesce over perhaps 2 billion more years into a single large elliptical galaxy, the stars within them so sparsely distributed that direct stellar collisions will be rare, but the disruption to the spiral structure of both will be total. Above the Milky Way comes the local group. The Milky Way and Andromeda are the two massive anchors of a gravitationally bound family of galaxies called the local group. It contains roughly 80 members in total, the two large spirals, and a collection of smaller dwarf and irregular galaxies orbiting around them. The entire local group spans approximately 10 million light-years. It is bound. It will not disperse with the expansion of the universe. Its members are held together and will remain together, continuing their mutual gravitational interactions for as long as the universe allows large-scale structure to persist. Above the local group comes the Virgo supercluster. The local group is one small gravitational cluster among many that together make up the Virgo supercluster, a larger assemblage centered on the Virgo cluster, a dense concentration of roughly 1,300 galaxies, lying approximately 65 million light-years from us. The Virgo supercluster, also called the local supercluster, spans about 110 million light-years. For most of the 20th century, this was considered the largest structure to which the Milky Way could be said to belong. Above the Virgo supercluster comes Laniakea. The Virgo supercluster is not a freestanding structure, but a single lobe of Laniakea, the supercluster whose full 500 million light-year extent was revealed only in 2014, when Tully and his team mapped the flows of galaxies rather than their positions alone. Laniakea contains an estimated 100,000 large galaxies. The Milky Way sits at its outermost edge. Above Laniakea comes the Pisces Cetus supercluster complex. Laniakea is itself a filament, one strand among several, within a larger coherent overdensity of matter, approximately 1 billion light-years in extent. This structure is not gravitationally bound in the way the local group is. It is too large and too diffuse for that. It is a feature of the large-scale cosmic architecture, a thickening of the web, distinguished from its surroundings by a marginally higher density of galaxy clusters and filaments. It spans roughly 1% of the diameter of the observable universe. Above all of that comes the observable universe itself, the sphere of space from which light has had time to reach us centered on the Earth, approximately 46.5 billion light-years in radius and 93 billion light-years in diameter. It contains an estimated 2 trillion galaxies. The entire Pisces Cetus supercluster complex, all 1 billion light-years of it, is a feature barely visible at the scale of the whole. Laniakea would be a faint smudge. The local group would be a point. Now read it back. A planet 12,742 kilometers across, orbiting a star. That star embedded in a cloud 1 light-year wide. That cloud part of a galaxy 100,000 light-years across. That galaxy, one member of a cluster 10 million light-years wide. That cluster, a lobe of a supercluster 500 million light-years across. That supercluster, a filament in a structure 1 billion light-years long. That structure, a minor feature in an observable universe 93 billion light-years in diameter. And the observable universe is not the universe. It is a cage of light and time, the region from which signals have had time to reach us since the universe began. What lies beyond it is not a wall. It is not empty. It is simply space from which the light has not yet arrived. And to understand why this cage has the size it does, why the number is 93 billion light-years rather than something else entirely, you need to understand something that happened 380,000 years after the Big Bang, when the universe crossed a threshold that made observation possible at all. Here is a question that seems simple until you think about it carefully. The universe is 13.8 billion years old. Light travels at a fixed speed, approximately 300,000 kilometers per second, the fastest anything can move. So shouldn't the observable universe be 13.8 billion light-years in radius? Shouldn't the boundary of what we can see be determined by how far light could have traveled since the beginning? The answer is no. And the reason it is no tells you something important about what the universe has been doing for the entire 13.8 billion years of its existence. Space is not a static stage on which matter moves. It is itself a physical thing, a fabric that can stretch. Since the Big Bang, the fabric of space has been expanding. Every point in the universe has been moving away from every other point, not because the galaxies are flying through space like shrapnel from an explosion, but because the space between them is growing. The galaxies are, in a sense, stationary in their local regions of space. It is the space itself that is enlarging, carrying them apart the way dots drawn on the surface of a balloon move apart when you blow it up, without any of the dots moving across the surface. This has a consequence that is counterintuitive but unavoidable. When a photon, a single particle of light, is emitted in the early universe and begins traveling toward us, it does not simply travel through static space. It travels through space that is simultaneously expanding. The photon is moving forward at the speed of light, but the distance between us and its source is growing at the same time. The photon arrives eventually, but by the time it does, the object that emitted it is enormously further away than it was when the light set out. The matter that emitted the oldest light we can detect, the cosmic microwave background, which we will come to in a moment, has been receding from us for the entire 13.8 billion years that its light has been in transit. That matter is now approximately 46 billion light-years away. Its light took 13.8 billion years to get here, but the source has meanwhile moved to 46 billion light-years. This is why the observable universe spans 93 billion light-years, the 46.5 billion on one side of us, and the 46.5 billion on the other, even though the universe is only 13.8 billion years old. Now, what is the oldest light we can detect? What is the wall at the back of the observable universe? Approximately 380,000 years after the Big Bang, the universe underwent a transformation that cosmologists call recombination, though the name is a historical accident. Electrons and protons were combining for the first time, not recombining. Before this moment, the universe was extraordinarily hot, extraordinarily dense, and completely opaque. Matter existed as a plasma. a roiling sea of charged particles, electrons and protons, moving too fast and too energetically to bind together into neutral atoms. Light could not travel freely through this plasma. Every photon was almost immediately absorbed or scattered by the charged particles around it. The universe was, in a physical sense, a fog. Light could not propagate across it. Then the universe cooled below about 3,000 degrees, and something changed. Electrons slowed down enough to be captured by protons. Neutral hydrogen atoms formed for the first time. And neutral atoms do not absorb photons the way charged particles do. Suddenly, the fog cleared. Light was free to travel. The photons that had been trapped in the plasma for the first 380,000 years of the universe's existence were released, and they have been traveling ever since. That light is the cosmic microwave background. It is the oldest electromagnetic radiation in the universe, emitted from every point on the surface of a sphere surrounding us, a sphere that marks the moment of recombination, the moment the universe first became transparent. The light from that surface has been traveling toward us for approximately 13.8 billion years. It arrives today at every point in the sky simultaneously, as a faint glow of microwave radiation corresponding to a temperature of approximately 2.7 degrees above absolute zero. It is not visible to the naked eye, but it is detectable with the right instruments, and it fills the entire sky uniformly. It was first detected accidentally in 1965 by Arno Penzias and Robert Wilson, two radio engineers at Bell Labs in New Jersey, who noticed an unexplained hiss in their antenna that pointed in the same direction, regardless of where they aimed it. They even cleaned out a nest of pigeons from the antenna, suspecting the birds might be responsible. The hiss remained. It was the leftover light of the Big Bang. Penzias and Wilson received the Nobel Prize in Physics in 1978 for the discovery. The cosmic microwave background has since been mapped in extraordinary detail. The COBE satellite in the early 1990s detected tiny temperature variations across the sky. WMAP, the Wilkinson Microwave Anisotropy Probe, refined that map in the 2000s. The Planck satellite produced the most precise map yet in the 2010s, measuring temperature variations of 1 part in 100,000. Variations so small that a thermometer accurate enough to distinguish them would need to resolve temperature differences of roughly 30 millionths of a degree. Those tiny variations are not noise. They are the seeds of every structure that exists today. The slightly denser regions of the plasma, where temperatures were fractionally higher at recombination, were the gravitational seeds that eventually accumulated into galaxy clusters. The slightly less dense regions became the voids. The entire large-scale structure of the universe, the filaments, the nodes, the voids, is encoded in the pattern of temperature fluctuations in a map of light that is 13.8 billion years old. The cosmic microwave background is the back wall of the observable universe. We cannot see further back in time than it, because before recombination, the universe was opaque. We can look all the way to that surface and no further. It is a hard limit, and it lies at a distance of approximately 46.5 billion light-years. But here is the more alarming boundary. The observable universe, the sphere defined by the cosmic microwave background and everything between it and us, is everything we can currently see. That is the particle horizon. 46.5 billion light-years in every direction. Within that sphere, we can receive information about events that happened in the past. The cosmic event horizon is different. It is much smaller and much more disturbing. The cosmic event horizon is the boundary beyond which any signal emitted now, any photon sent outward at this moment, at the speed of light, will never reach us, because space is expanding so fast that the signal can never bridge the growing gap. This boundary sits at approximately 16 billion light-years. 16 billion, not 46.5 billion. The reachable universe is far smaller than the visible universe. What this means is that most of the galaxies we can currently see are already beyond our reach. The light we receive from them now left billions of years ago, before they crossed the horizon. We see them because of light they sent in the past. But anything they do now, Any signal they emit today, any civilization they might harbor that might try to contact us, will never reach us. They have, in the only physically meaningful sense, already left our universe. We can see their past, but we share no future. And the list of galaxies we are permanently cut off from grows longer every year. As dark energy continues to accelerate the expansion of space, more and more galaxies are being pushed over the event horizon. The horizon itself is not moving. It sits at a fixed co-moving distance of approximately 16 billion light-years. But the galaxies beyond it are receding faster than light can follow, and the galaxies near it will eventually cross it too. One by one, the lights are going out. Not because the galaxies are dying, but because space is expanding too fast for their light to reach us. There is a quantity cosmologists call the future visibility limit, the outer boundary of everything we will ever be able to observe, not just now, but at any point in the infinite future, even if we waited forever. That boundary sits at approximately 62 billion light-years. Beyond it, space is and will always be forever inaccessible to us, not because of any limit in our instruments, because of the physics of space itself. Think about what that implies for civilizations in the far future. In 100 billion years or so, a timescale that is long but not infinite, dark energy will have pushed essentially all galaxies beyond our event horizon. Astronomers who exist in the Milky Way at that epoch, if the Milky Way still exists and anyone is there to look, will see a sky almost entirely devoid of other galaxies. The cosmic microwave background will have been redshifted by the expansion of space to wavelengths so long and so faint that it will be undetectable. There will be no evidence of the Big Bang visible in the sky. There will be no grand structure of superclusters and filaments visible through telescopes. The evidence that we are in a vast, structured, expanding universe will have been erased by the universe itself. Those future observers, if they existed, would have no way of deducing from observation what we can deduce today. They would conclude, based on the available evidence, that the universe consisted of a single island of stars in an otherwise empty void. The entire story of cosmic structure, the 2 trillion galaxies, the cosmic web, the Big Bang itself, would be hidden from them not by ignorance or limited instruments, but by the fundamental physics of an accelerating expansion. We are living in a window of cosmic history that is, in a very real sense, uniquely privileged. The evidence is here. The galaxies are visible. The cosmic microwave background is detectable. The story can still be read from beginning to end. At no earlier point in cosmic history were the instruments sensitive enough or the technology available to read it. At no later point, on a scale of tens of billions of years, will the evidence still be intact. Right now, in this narrow sliver of cosmic time, everything is in place for a species capable of the right kind of curiosity to piece together the full history of the universe. The universe is slowly, inexorably hiding its own history. We are lucky to be here now, when the story can still be read. And right now, the telescope that was supposed to confirm our understanding of that story has instead begun to fracture it. The James Webb Space Telescope launched on Christmas Day, 2021. It was the product of more than 20 years of development, the work of thousands of engineers and scientists across NASA, the European Space Agency, and the Canadian Space Agency. And at the time of its launch, it was the most complex scientific instrument ever sent into space. Its primary mirror, a honeycomb of 18 gold-coated beryllium segments, each the size of a dining table, that unfurl in space to form a collecting surface 6.5 meters across, is roughly 6 times larger in area than the Hubble Space Telescope's mirror. It observes primarily in infrared light, wavelengths invisible to human eyes, which allows it to peer through the gas and dust that obscure visible light and to detect the heavily redshifted glow of galaxies so distant that their light has been stretched by the expansion of the universe from ultraviolet and visible wavelengths all the way out into the infrared. Webb was built, in part, to find the first galaxies, the ones that formed in the first few 100 million years after the Big Bang, the ones that, according to our best models of how the universe evolved, should have been small, dim, and few in number. The raw, primitive building blocks from which larger galaxies gradually assembled over billions of years. The mission was, in a very real sense, a test of the standard model of cosmology. Point the most powerful infrared telescope ever built at the early universe and see whether the galaxies you find match what the equations predict. They do not. Before Webb launched, the standard model, known as lambda CDM, for the cosmological constant that represents dark energy and the cold, dark matter it assumes fills the universe, made predictions about what the early universe should look like. The model predicts that galaxies form slowly through a long process of gas collapse and stellar ignition and repeated mergers, and that in the first few 100 million years after the Big Bang, only a small number of small, faint, chemically simple galaxies should exist. The universe was new. There had not been enough time for stars to live and die in numbers sufficient to enrich the interstellar medium with the heavier elements that more complex galaxies contain. The model was clear, and it was built on decades of observations that seemed to support it. Then Webb began looking. The initial results, which started arriving in 2022 and have continued in the years since, showed approximately 100 times more bright, well-developed galaxies in the early universe than the model predicted. Not twice as many, not 10 times as many, 100 times. The galaxies Webb was finding were not just present in unexpected numbers. They were bright, which means they were forming stars at rates far higher than the models allowed for their age. They were massive, which means they had assembled far more stellar material than the timescales of the model should have permitted. And they were chemically enriched, which means the stars within them had already lived, burned through their fuel, and died, spreading heavier elements into the surrounding gas, all within a period that the standard model said was too short for that process to have run more than once. This is not the kind of discrepancy that goes away when you reprocess the data. It is not an instrumental artifact or a selection bias or a calibration error. The James Webb Space Telescope is extraordinarily well characterized. Its capabilities are well understood. The galaxies it is finding are real. On May the 16th, 2025, a team led by Rohan Naidu, an astronomer at MIT's Kavli Institute for Astrophysics and Space Research, used Webb's near-infrared camera, the NIRCam instrument, to image an object in the Cosmos survey field. The object had been seen in previous survey data as a candidate for a very high redshift galaxy, but it had not been spectroscopically confirmed. Naidu and 45 co-discoverers pointed Webb's near-infrared spectrograph at the candidate and measured its spectrum in detail. The result was unambiguous. The galaxy, designated MOM-Z14, after the survey field and its measured redshift, has a spectroscopic redshift of 14.44. Redshift is the stretching of light by cosmic expansion, and a redshift of 14.44 means that the light from MOM-Z14 was emitted when the universe was approximately 280 million years old, just 2% of its current age. The light took approximately 13.5 billion years to reach Webb's mirror. It is the most distant galaxy ever confirmed by spectroscopic measurement. The peer-reviewed paper, led by Naidu and his co-authors, was published on January the 28th, 2026, in the Open Journal of Astrophysics. What MOM-Z14 is, once you look at it carefully, should not be possible within the constraints of our standard model. It is extraordinarily compact. Its effective radius is approximately 240 light-years, roughly 1% the size of the Milky Way. A galaxy, in that sense, barely deserving the name in terms of physical extent. But within that tiny volume, it is producing stars at a prodigious rate, and the stars it has already produced have enriched the surrounding gas with a chemical complexity that takes multiple stellar generations to achieve. The spectrographic data shows strong nitrogen emission lines, a signature of highly enriched gas, at a level that would normally require at least one full cycle of massive stars forming, burning, and exploding as supernovae, scattering their heavier elements into the surrounding medium. Within 280 million years of the Big Bang, The standard model does not give those stellar generations enough time. The stars necessary to produce the nitrogen that MOEMZ14 displays should not yet have had time to be born, live, and die. Naidu's summary of what Webb has been showing the scientific community was precise and deliberate. He noted that with Webb, humanity is able to see further than ever before, and what it sees looks nothing like what was predicted, which he described as both challenging and exciting. Jacob Shen, a postdoctoral researcher at MIT and a member of the research team, put it more directly. There is, he said, a growing chasm between theory and observation related to the early universe. MOM-ZE14 is the record holder for the moment, but it is part of a pattern. The previous record-holding galaxy, designated JADES-GS-Z14-0, existed approximately 300 million years after the Big Bang, itself a record breaker when it was confirmed in the years before. MOEMZ14 pushed the observational frontier back a further 20 million years. Webb itself appears poised to push it back further still. As the telescope's surveys deepen and widen, more candidates at even higher redshifts are being identified. The researchers who found MOM-Z14 noted in their paper that previously unimaginable redshifts, approaching the era of the very first stars, no longer seem far away. There are other examples. Among the galaxies Webb has found in the early universe is a galaxy named Zhulong, a massive, well-formed spiral galaxy confirmed to exist at a redshift that places it approximately 1 billion years after the Big Bang. Spiral galaxies were not expected to exist in that form at that era. The standard model predicts a long, gradual assembly of structure from smaller, irregular pieces, with the smooth, disc-like shape of a spiral taking billions of years to settle into. Zhulong looks like a galaxy that formed quickly, efficiently, and with a structural regularity that our models say should not have been achievable so soon. It is another data point in a pattern that cosmologists are now taking very seriously. The pattern itself is the problem. A single anomalous galaxy could be an observational error, a misidentified object, a statistical outlier in a large and varied sample. Two anomalous galaxies might be a curiosity, but when a telescope systematically finds, across multiple independent surveys, in multiple different regions of the early universe, approximately 100 times more bright, massive, chemically complex, and structurally developed galaxies than the best available model predicts, that is not an anomaly. That is a signal. The scientific community is not in denial about this. The James Webb Space Telescope's findings have generated an enormous amount of activity in theoretical cosmology. Papers proposing explanations have been multiplying since the first unusual results arrived in 2022. The explanations span a wide range. Some argue that feedback mechanisms, the ways in which the energy released by the first stars and supernova affected the surrounding gas, were different in the early universe than the models assume, allowing star formation to proceed faster and more efficiently. Others suggest that the initial mass distribution of stars in the early universe was different, skewed toward heavier, shorter-lived stars that lived and died quickly, enriching their surroundings faster than the models predict. Others still suggest that dark matter behaved differently in the very early universe than it does today, or that the initial power spectrum of density fluctuations from which all structure grew had properties we have not correctly characterized. What does it mean for the standard model? There are several possibilities, none of which is comfortable in the way that confirmation would have been. The most conservative is that the models are broadly correct, but are missing some relatively straightforward physical process, that with better modeling of stellar feedback, gas dynamics, or the early history of dark matter clustering, the predicted galaxy counts would rise to meet the observations. This is the hopeful interpretation, a model that needs tuning rather than replacement. The more radical interpretation is that the assumptions about dark matter, dark energy, the initial conditions of inflation, and the rate at which structure assembled in the early universe all need revision at a level deeper than parameter adjustment. That the Standard Model, which has been extraordinarily successful at explaining an enormous range of observations, is nonetheless wrong about something important at its core. Both interpretations are actively being investigated. Neither has been ruled out. What is clear is that the James Webb Space Telescope has not confirmed our picture of the early universe. It has complicated it, perhaps irreversibly. The galaxies being found are too numerous, too bright, too massive, too chemically enriched, and too structurally developed for a universe as young as the one Webb is imaging. A factor of 100 is not what refining a parameter fixes. These findings are not isolated. They are connected to a crisis that runs even deeper and has become even more precisely measurable. The Hubble tension, the JWST galaxy density problem, the chemical enrichment anomalies, they are symptoms. And the symptom that has now crossed the threshold physicists use to declare a discovery, the one that can be stated as a single irreducible number, is a disagreement about the most fundamental property of the universe: how fast it is expanding, and whether our best models of the cosmos can survive the answer. Two numbers, that is all it takes. 67.4, 76.5. Both measured in the same units, kilometers per second per megaparsec, which means kilometers per second of recession speed for every 3.3 million light-years of distance between two objects. Both measuring the same thing: how fast the universe is expanding. Both derived from decades of careful, precise, independent observation by teams of scientists who have staked their professional reputations on the accuracy of their methods. They cannot both be right. The first number comes from looking backward in time. The European Space Agency's Planck satellite spent 4 years, from 2009 to 2013, mapping the cosmic microwave background, the ancient afterglow of the Big Bang, across the entire sky with extraordinary precision. The pattern of temperature fluctuations in that map, the tiny variations of 1 part in 100,000 that encode the state of the universe at the moment of recombination, allows cosmologists to infer the expansion rate by running the Standard Model of cosmology forward from those initial conditions. The answer is 67.4 kilometers per second per megaparsec. If this number is correct, then for every 3.3 million light-years of space, the universe is expanding at 67.4 kilometers per second faster. The second number comes from measuring distances directly in the local universe, the way you might measure a room with a tape measure, step by step, object by object, each measurement calibrated against the one before it. The method is called the cosmic distance ladder. On the lowest rung sit certain variable stars, Cepheids, which pulse with a period directly tied to their true brightness. By comparing how bright they appear from Earth with how bright they actually are, you can calculate their distance with high precision. From those nearby Cepheids, you step outward to more distant galaxies that contain both Cepheids and another class of objects, Type 1, a supernovae, that flare with a consistent peak brightness wherever they occur. The supernovae carry the ladder further, to distances where the redshift of galaxies becomes the primary tool, and the ladder as a whole gives you the local expansion rate. The SH0-ES collaboration, supernovae H0 for the equation of state, has been refining the cosmic distance ladder for many years with exactly this goal. Their measurements have consistently returned a value higher than the Planck number. In 2025, Dan Skolnick at Duke University and his colleagues added a new and unusually well-measured first rung to the ladder using the Coma cluster of galaxies. The Coma cluster, lying approximately 320 million light-years away, has been measured by dozens of independent teams over 4 decades, making it one of the most precisely characterized galaxy clusters in the sky. Skolnick's team used 12 Type 1a supernovae within the cluster to determine its distance with exceptional accuracy and used that as the anchor from which the rest of the ladder was calibrated. Their result, 76.5 kilometers per second per megaparsec, 67.4, 76.5, a discrepancy of approximately 9%. Skolnick himself described the situation bluntly. He noted that the scientific community has been pressing hard against models that have been in use for 2.5 decades, and that what they are seeing is those models not matching up. For years, the most charitable interpretation of the discrepancy was that one of the measurement methods contained a systematic error, a hidden bias, a miscalibration, a source of contamination that was pushing the result in one direction without anyone having noticed. The most obvious suspect was the local measurement. Cepheid variable stars are difficult to measure precisely in distant galaxies because they can be confused with neighboring stars in crowded stellar environments, and because dust between us and the galaxy can absorb some of their light, making them appear dimmer and therefore further away than they actually are. Either of these effects, if unaccounted for, could push the local Hubble constant upward. To test this, the James Webb Space Telescope was used in 2024 and 2025 to re-observe the same Cepheid stars that the local measurement programs had relied upon. Webb's superior resolution allows it to resolve individual stars in distant galaxies far more cleanly than any previous telescope, separating the target Cepheid from its neighbors and reducing the contamination effect. The results were unambiguous. Webb found that the crowding corrections applied to the Hubble Space Telescope data had been accurate. The Cepheid measurements were correct. The local value of the Hubble constant is not an artifact of instrument limitations. Then, in December of 2025, a third independent measurement arrived. The TD-COSMO collaboration, an international consortium of approximately 20 research institutions, published results in the journal Astronomy and Astrophysics on December 5, 2025. Their method used neither Cepheids nor the cosmic microwave background. It used gravitational lensing of quasars. When light from a distant quasar passes close to a massive galaxy between us and the quasar, the galaxy's gravity bends the light, splitting it into multiple images. The images arrive at slightly different times because they have traveled slightly different paths around the lensing galaxy. These time delays, measured precisely over years of monitoring, encode information about the geometry of the universe and the expansion rate. TD-COSMO applied this method to 8 strongly lensed quasar systems. Their result was consistent with the local distance ladder measurement, consistent with 76.5, not with 67.4, 3 independent methods. 2 of them agree, 1 does not. And the one that does not is derived from the early universe via the standard model of cosmology. By late 2025, the statistical significance of the discrepancy had reached 5 sigma. A 5 sigma result means the probability of the gap arising by random chance, by an unlucky combination of measurement errors across all methods simultaneously, is less than 1 in 3.5 million. This is the same threshold that was required before physicists announced the discovery of the Higgs boson. It is the gold standard of discovery in physics. The Hubble tension has crossed it. The scientific community has proposed a range of possible explanations, and it is worth walking through them carefully because each one illuminates how deep the problem goes. The most discussed candidate is early dark energy, a hypothetical form of energy that may have existed in the early universe before the era of the cosmic microwave background, decaying away shortly after and leaving no trace in the local universe today. If such energy existed, it would have altered the sound horizon, the characteristic scale of density waves that were frozen into the early universe as the primordial plasma cooled. The Planck analysis uses the sound horizon as a reference length, and if it were shorter than the standard model assumes, the inferred Hubble constant would be pushed upward toward the local measurement. Several theoretical papers have explored this model in detail, and it remains one of the more promising avenues. The difficulty is that adding early dark energy creates tensions elsewhere. It affects the predicted level of large-scale clustering of matter, a quantity measured by galaxy surveys, and those predictions move in the wrong direction when early dark energy is included. Fixing the Hubble tension with early dark energy tends to deepen another discrepancy, sometimes called the sigma-8 tension, about how clumped the universe's matter is on large scales. The universe does not yield its problems one at a time. Similar difficulties attend other proposed fixes, new light particles beyond the standard model of particle physics, which would have altered the radiation content of the early universe. Modified theories of gravity that behave differently from general relativity at large scales. Interactions between dark matter and dark energy that alter the expansion history. Each of these is theoretically motivated to some degree, and each has been studied seriously. Each faces constraints from other observations that prevent it from providing a clean, complete solution without creating new inconsistencies somewhere else in the cosmological ledger. The problem is structural. The standard model of cosmology, lambda CDM, is not just a collection of parameters. It is an interlocking framework in which the measurements of the early universe, the large-scale structure of galaxies, the abundance of light elements, and the local expansion rate are all tied together through a common set of physical assumptions. When you pull on one thread, the whole framework responds. A change that resolves the Hubble tension often tightens some other constraint. The model is very good, and that very goodness is part of what makes the tension so alarming. A model this tightly constrained should not have a 9% disagreement between its early universe prediction and 3 independent local measurements. And there is one more candidate that we have visited already in this journey. The KBC void, the underdense region approximately 2 billion light-years across in which the Milky Way appears to sit, could in principle contribute to the discrepancy. Galaxies inside an underdense region are gravitationally attracted toward the denser walls surrounding it, giving them a net outward motion that adds to the cosmological expansion. If the Milky Way sits inside such a region, then the local galaxies used to calibrate the distance ladder are moving outwards slightly faster than average, making the inferred local Hubble constant higher than the true global value. The mathematical effect is real, well understood, and not disputed. The question is magnitude. Current analyses suggest the KBC void might account for a few percent of the discrepancy, not the full 9%. It is a partial explanation, a contribution, but it is not a resolution. No proposed resolution has prevailed. Every candidate either leaves part of the gap unexplained or resolves the tension only by introducing new problems elsewhere. The standard model continues to provide the wrong answer by a statistically decisive margin when it is applied to the early universe and asked to predict what 3 independent local methods consistently find. 2 numbers, 67.4 and 76.5, measured with extraordinary precision, measured independently, measured by 3 different methods using 3 different physical principles, and they disagree. The universe is not giving us a consistent story about its own expansion rate. Either our model of the early universe contains a significant error, or our model of the local universe contains a significant error, or both. Either way, something in the foundation of modern cosmology is not right. And if our model is wrong about how fast the universe is expanding, it is worth asking what else it might be wrong about, including perhaps how big the universe actually is. Because what lies beyond the boundary of what we can observe may be far stranger and far larger than the 93 billion light-years we have been navigating. The observable universe ends 46.5 billion light-years from Earth in every direction. Not because space ends there, not because there is a wall, a boundary, a void on the other side. It ends there, from our perspective, at this moment, because light has not had time to reach us from any further away. The universe is 13.8 billion years old. Any photon emitted beyond that boundary, no matter how long ago, simply has not had enough time to cross the intervening space and arrive at our telescopes. The limit is in our clocks, not in the cosmos. And beyond that limit, space almost certainly continues. The question that physicists have been trying to answer, with varying degrees of success, is how far it continues. And the tools they have brought to bear on that question produce answers so large that the 93 billion light-years of the observable universe begins to seem not just small, but irrelevant. The first clue comes from geometry. When you look at the cosmic microwave background, the ancient light of the early universe, mapped in extraordinary detail by the Planck satellite, You are looking at light that has been traveling for approximately 13.8 billion years. The pattern of temperature fluctuations in that light contains information about the geometry of the space through which it has been traveling. Waves of sound, propagating through the early universe's plasma before recombination, left their imprint as a characteristic scale in the distribution of temperature variations, what cosmologists call the acoustic scale. If the universe is curved, if space bends back on itself the way the surface of a sphere does, then the acoustic scale, as seen in the CMB, would appear magnified or compressed, depending on the direction of curvature. If space is flat, geometrically flat, like a Euclidean plane extending infinitely in all directions, the acoustic scale would appear at its true size. The Planck measurements show that the universe is flat to within approximately 0.5%. This is a very tight constraint. What does it mean? In general relativity, the geometry of space depends on its energy density. A universe whose energy density is exactly equal to a critical value, called the critical density, will be geometrically flat. A universe with more than that density will be positively curved, like the surface of a sphere, eventually bending back on itself and being finite. A universe with less than that density will be negatively curved, like the surface of a saddle, and will be infinite but shaped differently. A flat universe sits precisely at the boundary between these two cases. And a flat universe, according to general relativity, is either exactly at the critical density, in which case it extends infinitely in all directions, or so close to it that the curvature is too small for any currently feasible measurement to detect. The flatness of the universe is not a coincidence. It is a prediction of inflation, the period of extraordinarily rapid expansion in the first tiny fraction of a second after the Big Bang. Any initial curvature in the early universe, however extreme, would have been stretched by inflation into near-perfect flatness, the way inflating a balloon makes its surface appear flatter the larger it gets. The flatness we observe is, in this sense, evidence for inflation. And if the universe is flat, it is in all likelihood infinite. An infinite universe creates a set of implications that are deeply uncomfortable to sit with. In a finite volume, even a very large one, only a finite number of distinct arrangements of matter are possible. The laws of quantum mechanics impose a limit on how precisely particles can be positioned and how closely they can approach each other, which means that within any finite volume, there are a finite number of distinct configurations. In an infinite universe, every possible configuration of matter permitted by the laws of physics is realized infinitely many times, not once, not occasionally, infinitely many times, spread across infinite space. This means that in an infinite universe, there is not just one region of space identical to the observable universe. There are infinitely many. The distance to the nearest identical copy of our observable universe, assuming inflation and a flat geometry, can actually be estimated, though the answer is not physically meaningful in any practical sense, because no signal could ever cross such a distance. But the mathematics is real, and its implication is this. Somewhere in infinite space, there is a region containing an identical copy of the Milky Way, an identical copy of the solar system, an identical copy of Earth, and an identical copy of you. Not approximately identical, identical in every quantum detail. Most physicists find this conclusion either fascinating or horrifying, depending on temperament. What almost all of them agree on is that it is untestable. We cannot observe beyond the observable universe. We cannot verify the existence of our quantum duplicate. The prediction of infinite copies is a logical consequence of certain assumptions. Infinite flat space, quantum mechanics, but it lies permanently outside the reach of any possible experiment. In 2011, a team of cosmologists, led by Mihran Vardanyan at the University of Oxford, brought a more measured but still arresting approach to the question of the universe's size. Rather than asking how well any single model fits the observational data, Vardanyan and his colleagues used a technique called Bayesian model averaging, which weights the predictions of all possible models by how probable each model is given the full body of available evidence. The technique prevents any one model from being artificially favored simply because it has been more extensively tested. Applied to the combined data from the cosmic microwave background and Type 1a supernova surveys, their analysis found that the universe is at least 250 times larger than the observable universe, at minimum, probably much more. This corresponds to a total diameter of at least 7 trillion light-years, and that is the lower bound from a conservative analysis, not an estimate of the likely value. 7 trillion light-years against the observable universe's 93 billion. The observable universe is less than 1 part in 250 of the whole, by the most cautious available estimate. Then there is the calculation that follows from inflation itself. Alan Guth at MIT proposed the theory of cosmic inflation in 1981, and it has since become the most broadly accepted explanation for the large-scale uniformity, flatness, and structure of the observable universe. The inflationary model describes a period of exponential expansion that occurred in the first tiny fraction of a second after the Big Bang, an interval of roughly 10 to the power of negative 35 seconds during which the universe expanded by an enormous factor. Working backward from this expansion, from the size and properties of the observable universe today, and from the expected duration of the inflationary period, Guth calculated that the full universe should be at least 10 to the power of 23 times larger than the observable portion. 10 to the power of 23. That is a 1 followed by 23 zeros. It is 100,000 billion times the diameter of the observable universe. It is worth being honest about the uncertainty here. Guth himself described this as highly uncertain, because the answer depends sensitively on the duration of the inflationary period and on the decay rate of the false vacuum, the energy state that drove inflation, both of which depend on the details of a grand unified theory of particle physics that we do not yet have. The number is a lower bound derived from a specific set of assumptions about the inflationary model's parameters, and it could be much larger. It could be infinite. It is not a measurement. It is a calculation from a model that we believe is broadly correct but have not proven in detail. What it is, however, is a statement about scale that should give pause. Even if the universe is only 10 to the power of 23 times larger than the observable portion, the most conservative inflation-based estimate, then everything we have discussed tonight, every galaxy, every filament, every void, every supercluster, every structure in the observable universe, all of it together occupies a fraction of the full universe so small that no number we routinely use carries any meaning at that scale. The observable universe, with its 2 trillion galaxies, and its 10 to the power of 24 stars, and its Hubble tensions, and its dark energy, and its cosmic web, is a drop. The ocean may be infinite. We are somewhere on its surface, in a particular drop, with instruments capable of seeing only the drop we are in, trying to deduce from its properties what the rest of the ocean is like, whether space goes on forever or stops at some finite boundary. That question cannot currently be answered. What we can say, with some confidence, is that what lies beyond the observable universe is likely to be far more than we can observe, and almost certainly more than we have ever imagined. If inflation produced our observable universe as one bubble in an enormous expanse of space that continued to expand, what happened to the regions of that space where inflation did not stop? What came out of them? This is not a metaphor. This is what the physics of inflation, taken seriously, predicts. And it has a name. Inflation happened. The evidence is overwhelming that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion, a near instantaneous stretching of space that smoothed out the universe's geometry, seeded the density fluctuations that became every galaxy and void and filament we have mapped, and left in the cosmic microwave background a specific, detailed, testable signature. The Planck satellite measured that signature. It matched. The flatness of the universe, the scale invariant spectrum of density fluctuations, the overall uniformity of temperature in the CMB across regions of the sky that could never have been in causal contact without inflation. All of these observations point in the same direction. Inflation is not a certainty. It is a framework, and several of its details remain contested. But the broad picture is the best available explanation for the universe we observe, and most working cosmologists accept it. Here is what that acceptance implies. The mechanism that drives inflation, the physical process by which space expands exponentially, is governed by a quantum field. Like all quantum fields, it is subject to quantum fluctuations, tiny, random variations in its value that are an unavoidable consequence of the uncertainty principle. In most regions of space, these fluctuations cause inflation to end. The field's energy drops, inflation stops, and ordinary matter and radiation are produced as the energy of the inflationary field is converted, the process called reheating, into the hot, dense plasma that we recognize as the starting point of the standard Big Bang cosmology. A pocket of space ends its inflationary phase, and a universe begins. But here is the complication. In some regions, the quantum fluctuations push the field upward rather than downward. In those regions, inflation does not end, it continues. And because inflating space expands exponentially, the volume of space that is still inflating grows faster than the volume that has stopped. More regions nucleate universes. More regions continue to inflate. The process is self-sustaining. Inflation, once it starts, keeps producing new pockets of space where inflation ends, and therefore keeps producing new universes, while the ocean of inflating space between them keeps growing without bound. This is eternal inflation. And if inflation happened at all, eternal inflation is likely to be its natural consequence. Each of those pockets, each bubble of space where inflation ends and reheating occurs, is, in this picture, a universe of its own. Our observable universe is one such bubble. The Big Bang was not the beginning of everything. It was the moment of reheating in our particular bubble. Other bubbles, other Big Bangs, other universes are forming continuously in the inflating space outside and around us, in directions that have no physical meaning within our own space-time, because the inflating region and the reheated regions are causally disconnected from each other. We cannot see them. We cannot communicate with them. We cannot, even in principle, verify that they exist. This is the multiverse, not a concept invented to speculate about parallel realities, a mathematical consequence, uncomfortably direct, frustratingly untestable, of the physics that best explains the universe we observe. The string landscape deepens the picture. String theory, the most ambitious attempt to unify general relativity and quantum mechanics, predicts an enormous number of possible vacuum states, ways in which the universe's underlying quantum fields can arrange themselves at their lowest energy configuration. Estimates put this number at 10 to the power of 500 or more. Each vacuum state corresponds to a different set of physical constants, a different mass for the electron, a different strength for gravity, a different value for the energy density of empty space. In a pocket universe governed by a different vacuum state, the proton might be lighter or heavier, the electromagnetic force stronger or weaker, the chemistry entirely alien. Some of those universes would collapse within seconds. Others would expand so fast that no structure could ever form. In the string landscape multiverse, our physical constants are not uniquely determined by fundamental law. They are the local conditions of our particular bubble, and we observe the values we observe partly because they are the values compatible with observers. There is one potential observational signature of the multiverse that has not yet been ruled out. If our universe is a bubble in an inflating sea, neighboring bubbles would occasionally have collided with ours in the earliest moments after our Big Bang. The collision would have deposited energy in the boundary region between the two bubbles, and as our universe expanded and cooled, that energy would have been diluted and redshifted into the cosmic microwave background. The signature would be visible as a circular pattern of temperature anomalies on the CMB sky, a disk, roughly, where the temperature differs from its surroundings in a specific, predicted way. Cosmologists have searched for these signatures. Several candidate features have been identified and examined. None has been confirmed as a bubble collision. The most recent, most detailed analyses of the Planck data found no statistically significant evidence. The search is not over. Future CMB experiments with greater sensitivity may be able to detect subtler signals, but the current data do not reveal the multiverse. In March of 2018, 10 days before his death on March the 14th, Stephen Hawking submitted a paper for publication in the Journal of High Energy Physics. The paper was co-authored with Thomas Hertog, a physicist at KU Leuven in Belgium, who had collaborated with Hawking on aspects of this work for many years. The paper was Hawking's attempt to resolve a problem he had identified within his own earlier framework, the no-boundary proposal that he and James Hartley had developed in the 1980s. That proposal described the beginning of the universe in terms of quantum mechanics, but when others worked through its implications for inflation, they found that it predicted an infinite, fractal multiverse, a structure so vast and so varied that it was incapable of making any testable predictions about what any particular universe should look like. Hawking found this unsatisfying. As he put it, he had never been a fan of the multiverse. If the scale of different universes in the multiverse is large or infinite, the theory cannot be tested. Hawking and Hertog used a mathematical technique called holography, drawn from string theory, to revise the framework. Their approach collapsed the time dimension of eternal inflation onto a spatial boundary, a kind of cosmic surface, and derived from that boundary a description of what universes should emerge from the inflationary process. The result was a multiverse that, rather than being infinite and structurally fractal, was finite, countable, and dominated by universes similar to our own. It was a framework that, at least in principle, could be tested, not by direct observation of other universes, but by the predictions it makes about the specific properties of our own, particularly the pattern of primordial gravitational waves imprinted on the cosmic microwave background. The paper was published on May 2nd, 2018. It is important to be accurate about what it established. Avi Loeb, a theoretical physicist at Harvard, was among those who pointed out that the paper's central conclusion is a conjecture, not a mathematically proven result. The framework is stimulating and the reasoning is serious and original, but the mathematical tools it employs involve approximations and assumptions that have not been rigorously justified in the full physical context. It is not a confirmation that the multiverse exists. It is not a measurement. It is a theoretical framework, representing one possible way to make multiverse theory more tractable and less infinitely speculative, and it is a framework that remains to be tested. The primordial gravitational wave signature that Hertog identified as the potential smoking gun has not been detected. The deeper problem is one that no paper has resolved, and that the Hawking-Hertog framework only partially addresses. A theory that predicts infinitely many universes with infinitely varied properties, in which every conceivable outcome is realized somewhere, makes no falsifiable predictions about what any particular universe should look like. Every observation is consistent with such a theory, because every observation is realized somewhere in the infinite ensemble. A theory consistent with everything is, in the strict sense of the word, a theory that explains nothing. It is a framework, a container, a space in which more specific theories might eventually be placed. But it is not, in its present form, science in the way that the predictions of general relativity or the standard model of particle physics are science. The boundary between physics and philosophy is somewhere in this territory, and physicists disagree about exactly where to draw it. Some are comfortable treating the multiverse as a legitimate physical hypothesis, to be refined and eventually constrained by observations of our own universe. Others insist that a hypothesis incapable even in principle of direct verification is not a physical hypothesis at all. Both positions are held by serious people with deep knowledge of the subject. What seems clear is that we are at the edge, not the edge of the universe. The universe may have no edge. The edge of what we can currently know. The boundary between the questions physics can answer and the questions it has so far only learned to ask. One bubble in an inflating sea, with its own Big Bang, its own constants, its own 2 trillion galaxies, its own cosmic web, its own dark energy pushing everything apart. And within that bubble, on one thin filament, in one ordinary galaxy, on one rocky planet, something asking what else is out there. That question has a very specific form, and it is the oldest question our species has ever asked. Let us talk about the numbers. The Milky Way is 100,000 light-years across. It contains somewhere between 200 and 400 billion stars. Of those stars, conservative estimates suggest that tens of billions orbit at distances that could, in principle, support liquid water on an orbiting planet, the condition most associated with the chemistry of life as we know it. The universe has been producing stars and planets for approximately 13 billion years. Life appeared on Earth within a few 100 million years of the planet's formation, early by geological standards, suggesting that given the right conditions, chemistry finds its way to biology without undue difficulty. If even a small fraction of the tens of billions of potentially habitable planets in our galaxy gave rise to life, and if even a fraction of those went on to produce complex organisms, and if even a fraction of those produced intelligence, and if even a fraction of those intelligence developed technology capable of transmitting signals across interstellar distances, then the galaxy should, by any reasonable reckoning, be populated with civilizations. The numbers demand it. The universe has had billions of years and billions of opportunities to produce beings capable of reaching across the void, and yet, silence. We have been listening with increasing sophistication for roughly 7 decades. Radio telescopes have been scanning the sky for signals of non-natural origin since the early 1960s. The search has been patchy, incomplete, not nearly as comprehensive as the problem deserves, but it has also been real, and it has found nothing. No confirmed signal, no structured transmission, no beacon, no leakage radiation, no indication that any other technological civilization has ever sent so much as a whisper in a direction that happened to include us. Beyond radio searches, astronomers have catalogued the infrared signatures of hundreds of thousands of galaxies, looking for the waste heat that a civilization of sufficient scale would necessarily radiate. They have looked for stars being dismantled for raw materials, for megastructures blocking the light of stars in unusual periodic patterns, for anything that would indicate intelligence operating at a scale detectable across interstellar or intergalactic distances. Nothing. In 1950, the physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos National Laboratory in New Mexico. The conversation had turned to flying saucers, which were a popular topic that summer. Into the discussion, Fermi dropped a question that has never been adequately answered. Where is everybody? Given the age and size of the universe, given the timescales available, given the ease with which life appeared on Earth, the absence of any detectable evidence for intelligence beyond our planet is a problem. It is called the Fermi paradox, and it first appeared in published form in a footnote of a 1963 paper by Carl Sagan. There are 3 broad categories of explanation for the silence, and they differ not just in their content, but in what they imply for us. The first is structural. The silence may simply be a consequence of the distances and timescales involved, with no sinister implication at all. The nearest star to our Sun is approximately 4.2 light-years away. A radio signal sent from Earth today would arrive there in 4.2 years. Any reply would take another 4.2 years. If there were a civilization at Alpha Centauri capable of responding, we would wait nearly 9 years for a conversation we could hold in real time on a telephone. At greater distances, the delays compound. A signal from the far side of the Milky Way, 50,000 light-years away, would take 50,000 years in each direction. A civilization that flourished and went silent 50,001 years ago would have no overlap with our listening window. The galaxy is vast. The history of intelligence on Earth is recent. We have been broadcasting for roughly a century. The sphere of space into which our oldest radio signals have reached is only about 200 light-years in diameter, a tiny bubble in a galaxy 100,000 light-years across. We may simply not have been listening long enough, or with enough sensitivity, or in the right directions, or at the right frequencies. The absence of a detected signal does not, on this view, require the absence of signalers. This is the most comfortable explanation. It asks nothing of us except patience. The second is the Great Filter. In 1996, an economist named Robin Hanson published a paper arguing that the silence points to the existence of some barrier, a filter, through which the overwhelming majority of life-bearing worlds fail to pass on their way from simple chemistry to a spacefaring, galaxy-spanning civilization. The filter is not a physical wall. It is a step in the developmental sequence that is so difficult, so improbable, so catastrophically likely to fail that almost nothing survives it. The terrifying question is whether that filter lies behind us or ahead. If the filter is behind us, if the hard step was the emergence of life itself, or the development of the eukaryotic cell, or the evolution of complex multicellular organisms, or the emergence of intelligence, then we may have already passed it. We may be among the tiny fraction of lineages that made it through. The silence would reflect our rarity, not our doom. We would be the lucky ones, perhaps the only ones in the galaxy, and that would be remarkable rather than threatening. If the filter is ahead of us, the calculation is very different. If civilizations consistently fail to survive beyond a certain threshold of technological development, if nuclear weapons or engineered pathogens, or the uncontrolled development of artificial intelligence, or some other consequence of advanced technology, reliably end civilizations before they can become detectable, then the silence is a warning. The absence of signals would be evidence of what awaits. Every civilization in the galaxy that reached our level of technology subsequently vanished. We are next in line. On this reading, the Fermi paradox is not just a scientific curiosity, it is a data point about our own survival. The discovery of life on Mars, or on any other world in our solar system, would, on the Great Filter interpretation, be cause for concern rather than celebration. If life arose independently on two planets in the same solar system, then the emergence of life is easy. Whatever the filter is, it is not the origin of life. It must be something later, something we have not yet passed. The third category is the dark forest. In 2008, the Chinese science fiction author Liu Cixin published a novel whose central idea has since been taken seriously in academic discussions of the Fermi paradox, though versions of it predate his work. In 1983, the astronomer David Brin had explored a related concept under the name of deadly probes. The idea is this: civilizations exist, perhaps in large numbers, but any civilization that announces its presence risks destruction by a more technologically advanced one. The rational strategy for any civilization that has reasoned through the situation is silence. You listen, but you do not speak. You observe, but you do not signal. The universe is not empty. It is quiet. And it is quiet not because nothing is there, but because everything that is there has learned, through necessity or logic, to make no sound. The universe, on this view, is a dark forest in which every hunter moves without noise, and the only civilizations still alive are the ones that never revealed themselves. It is a deeply unsettling picture, and it is not the only interpretation of the silence, and there are serious objections to it. Game theoretic analysis suggests that the equilibrium of universal concealment is fragile, that there are circumstances under which cooperation would be advantageous, and that a sufficiently old and stable civilization might find ways to signal safely. The assumption that any detected civilization would necessarily be destroyed rather than contacted is an assumption, not a deduction, and the dark forest hypothesis, like the others, is untestable in any direct way. There is a fourth framing that does not require other civilizations to be rare or afraid. It requires only that the universe be the size it is. The observable universe spans 93 billion light-years. Even within the Milky Way, the distances between stars are measured in light-years. A signal sent from a civilization that evolved and reached technological sophistication 100,000 years ago in a galaxy whose average stellar separation is several light years, might simply not have reached us yet, or it might have passed us before we were listening, or it might be arriving now in frequencies we are not monitoring, or in encoding schemes we have not thought to look for. The architecture of the cosmos, the sheer scale of the distances, the finite speed of light, the brevity of any one civilization's existence relative to the age of the galaxy, may be sufficient to enforce a silence that feels absolute, but is simply geometric. The universe may not be built to keep life rare. It may be built in such a way that even common life is permanently isolated by the time it takes light to travel. The silence is consistent with all of these explanations. It does not, on the evidence currently available, allow us to choose between them. That is a genuinely unresolved situation, and it is worth sitting with. The oldest question our species has ever asked, are we alone, remains, after 70 years of increasingly sophisticated searching, unanswered. The silence is real. What it means is not yet known. Maybe it is a mystery to be solved when our instruments improve and our search methods broaden. Maybe it is an early warning that we have not yet learned to read. Maybe it is the natural state of a universe so large that intelligence, however common, never makes it across the void in time to find itself. Maybe the universe is vast enough that everyone is alone, even if no one is alone. That is a lonely thought, but it is not the last thought. Because everything that has been described tonight, every distance measured, every galaxy catalogued, every void mapped, every crisis in our model of the cosmos identified and named, was accomplished by something that should not, by any reasonable cosmic accounting, exist at all. On February 14th, 1990, at the request of Carl Sagan, the Voyager 1 spacecraft turned its camera around. Voyager had been traveling for 12 years by that point, outward and away from the Sun at about 60,000 kilometers per hour, on a trajectory that would carry it eventually into interstellar space. It had completed its scientific mission years earlier, photographing Jupiter and Saturn and their moons in unprecedented detail. Its cameras had been switched off to conserve power. Sagan had been arguing since the mid-1980s that before they were shut down permanently, the cameras should be turned back toward the inner solar system for one final look at the world that built the spacecraft. The resulting image, 60 frames composited together, taken when Voyager was approximately 6 billion kilometers from Earth, shows the solar system's planets as faint points of light against the deep black of space. Earth is there. It is a pale blue dot, less than 1 pixel in size, suspended in a ray of scattered sunlight created by the camera's optics. It is almost invisible. Most people, shown the image for the first time, have to be told which pixel is Earth. Sagan wrote about that image for years. He described how everything we have ever known lives on that pale dot. Every king and peasant, every saint and sinner, every young couple in love, every mother and father, every act of heroism and every act of cruelty, every civilization that rose and every civilization that fell, every teacher and every student, every inventor and every explorer. Every human being who has ever lived was born and lived and died on that vanishingly small point of reflected light. The photograph was taken from a distance of 6 billion kilometers. In cosmic terms, that is almost nothing. Voyager had not yet crossed one light day. It had not yet left the solar system's gravitational domain, and already, from that trivial remove, Earth was invisible. Now we know what the photograph could not show. That pale blue dot orbits a star, one of an estimated 250 billion in the Milky Way galaxy. The Milky Way is 100,000 light-years across, a barred spiral galaxy embedded in a dark matter halo with a 4 million solar mass black hole at its center. That galaxy is one of perhaps 2 trillion in the observable universe, gathered into groups and clusters and filaments and superclusters, separated by voids 300 million light-years wide. The Milky Way sits at the outer edge of Laniakea, a supercluster 500 million light-years across, itself a filament in a complex of superclusters stretching over 1 billion light-years, which is roughly 1% of the observable universe's diameter. The observable universe itself is 93 billion light-years across and is almost certainly a small fraction, perhaps an inconceivably small fraction, of the full extent of space. Every layer of that address was unknown to the person who took the photograph. Voyager did not know it. The camera did not know it. The pale blue dot suspended in the sunbeam did not know it. But you know it. And here is the thing that the photograph also could not show, though it is true of every atom in the spacecraft and every atom in the planet and every atom in you. The hydrogen in the water that fills your cells, the oldest atom, the simplest atom, one proton and one electron, was forged in the first 3 minutes after the Big Bang, when the universe was a roiling plasma of protons and neutrons, and the temperature was still 1 billion degrees. That hydrogen has been here for 13.8 billion years. It existed before the first star, before the first galaxy, before the first void. It predates every structure in the universe we have described tonight. And it is in you. The carbon in your body, the backbone of every biological molecule, the atom without which no chemistry resembling life as we know it is possible, was not produced in the Big Bang. It was produced inside stars. Stars that formed, burned for millions of years, swelled into red giants, and expelled their outer layers in slow stellar winds or violent explosions, scattering carbon into the interstellar medium, where it eventually became part of a molecular cloud that eventually collapsed into a new star, our Sun, and its surrounding disk of material, from which the Earth and you eventually emerged. The carbon in your body has passed through at least one stellar interior before it reached you, possibly several. The iron in your blood, the atom at the center of hemoglobin, the molecule that carries oxygen from your lungs to your cells, was forged in the catastrophic death of a massive star. Iron is the end product of stellar fusion. When a star's core fills with iron, fusion stops. The star collapses in milliseconds, and the outer layers are blasted into space in a supernova explosion visible across entire galaxies. The iron in your blood was assembled in the final moments of a star that died before the sun existed, scattered into the galaxy, gathered again into the cloud that formed the solar system, incorporated into the Earth, and then, across billions of years of chemistry and geology and biology, found its way into you. The calcium in your bones was assembled in the same kind of dying star. The oxygen you breathe was produced by ancient bacteria that, over roughly 2 billion years, transformed the composition of the Earth's atmosphere. The nitrogen in your proteins was fixed from the air by microorganisms that have existed since the early history of life on Earth. You are not visiting the universe. You are not a passenger. You are not separate from the matter and the processes we have been describing tonight. You are a specific arrangement of 13.8 billion-year-old matter, assembled by the physics of nuclear fusion and supernova explosions and planetary chemistry and biological evolution, and you have arrived, for this brief interval, at a configuration capable of asking questions. Hydrogen, given 13.8 billion years, became something that could wonder about hydrogen. The universe is 13.8 billion years old. For most of that time, it was opaque, then cooling, then dark, then slowly brightening as the first stars formed in the first few 100 million years, then filling with galaxies, then organizing those galaxies into the cosmic web that now spans the observable universe. For the first 9 billion years, there was no Earth. For the first 9.5 billion years, there was no sun. For the first 13.25 billion years, there were no animals with brains capable of forming questions. For the first 13.799 billion years, give or take, there was no one reading a sentence like this one. The cosmic web wove itself in silence. The Botas void expanded for 330 million years without a single observer inside it to register its emptiness. The filaments of gas and dark matter connected their quasar-host galaxies across 3 million light-years before any instrument existed to photograph them. The cosmic microwave background has been traveling for 13.8 billion years, encoding the entire early history of the universe in its temperature fluctuations, waiting for something capable of mapping it. And then, on one thin filament, in one galaxy, in one solar system, on one rocky planet, something crossed a threshold. Atoms arranged themselves into configurations that could process information, respond to their environment, model the future, ask about the past. Eventually, they built telescopes. Eventually, they pointed them at the ancient light of the cosmic microwave background and read the story of the universe's first moments. Eventually, they measured the expansion rate and found it cracked. Eventually, they looked back 280 million years after the Big Bang and found a galaxy that should not exist. We are the part of the universe that knows how large the universe is. That is not a trivial statement. The Bottas void is 330 million light-years wide, and it does not know it is empty. The cosmic web stretches across the observable universe, and it has never seen itself. The 2 trillion galaxies in the observable universe contain 10 to the power of 24 stars, and without observers, that number is just a number, a quantity unrealized, unremarkable, experienced by no one. What makes a number real, in any meaningful sense, is something that can apprehend it. And right now, in this narrow window of cosmic history, that something is here. The window is narrowing. In 100 billion years, dark energy will have pushed every other galaxy over the cosmic event horizon. The cosmic microwave background will be too cold and too redshifted to detect. Future civilizations, if any exist, will look out into what appears to be an empty universe and will have no way of knowing it was not always so. The evidence will be gone. The story will be illegible. The window will have closed. We are in it now. The distant galaxies are still visible. The CMB is still detectable. The structure of the universe, its filaments and voids and superclusters, and the crisis in our model of how it all works, can still be pieced together by beings with the right instruments and enough patience. Every observation described tonight was made in this window by beings assembled from the wreckage of dead stars, standing on a rocky planet orbiting a middle-aged star in an unremarkable spiral arm of one galaxy among 2 trillion. We are small, impossibly, vertiginously small. By every measure of size and distance and time that the universe provides, we are negligible. A virus on a grain of sand on a beach that stretches further than light has ever reached. And we are the part of the cosmos that knows this. That knowing is not nothing. It is, by any measure that might actually matter, the most extraordinary thing the universe has produced. Not in meters, not in light years, not in the units of scale we have been using all night. In meaning. The universe spent 13.8 billion years building the conditions for atoms to cross the threshold into awareness. And here, in this narrow moment, they have. Beings capable of measuring 93 billion light-years of reality from a planet 12,742 kilometers in diameter. Beings capable of identifying a galaxy that existed 280 million years after the beginning of time, and knowing it should not be there. Beings capable of standing inside the problem and asking the right questions. The universe is not looking at itself through a telescope pointed outward. It is looking at itself from inside. From this pale blue dot, suspended in a sunbeam, at the end of a 12-year journey that crossed less than 1 light day of a universe 93 billion light-years wide. The universe is looking at itself and wondering what it means.